the last day of our GIAN program under the title Recent Trends in Metrical Fixed Point Theory and Applications. Our foreign experts, Romanian expert, Professor Vasile Brende, who is with us, Professor Veermani from Chennai, IIT Madras, he is also with us. So all the participants, students of PG of our department, I welcome you all. We have today overall, I can say 4 sessions including the valedictory. Starting from right 9:30, it is slightly delayed due to some preoccupation of some of participants. The first 2 lectures by our expert, Professor Brende, and after that, since I may be busy, after that because of the validity function, so I request sir, so I will just describe certain things, what left yesterday, and once we finish our lunch, after the lunch, we come for the session of Professor Veermani, and then we start for, after that, validatory function. You can collect your certificates. Your feedbacks are highly needed. Those feedbacks you have taken yesterday, kindly submit by today, because feedbacks gives a lot of strength, motivation, as well as the improvement to develop the GIAN programs, that what the participants or the research scholars or the students needed and what the host institution provided to them. So once again, I welcome you all and thank you very much for your all the participating days for this GIAN program. So let me invite Professor Brende for his lecture. Professor Brende.
Thank you. I will start by drawing your attention to the role of average and mean in this particular situation. So, previous days the talks started at 10. For today the schedule was 9:30, and what it resulted, we started at 9:45, which is the average of the 2 hours. So this is also a situation where we have this average applied concretely in a practical situation. Today I want to speak about error analysis of fixed point iterations. If you got a copy of my book, there is a chapter there which is devoted to this, this topic. What is error analysis? I'll try to give you some insights by means of two main concepts. So, rate of convergence and stability of iterative fixed point iterations. So, both are very important in concrete applications. And I'll start with some motivation about the role of iterative schemes in applied mathematics. I spoke already about this. Then applied fixed point iterative methods, and also I also mentioned during my previous talks the role of schemes in applied mathematics. As you know, only a few problems in applied mathematics can be solved exactly. So this is why we solve approximately, and to this aim we need mathematical numerical methods. Amongst the most important such numerical methods, we have these fixed point iterative schemes, which mainly come from this theory of iterative schemes. We can get starting from the equivalent fixed point problem into which we convert a certain problem. My intention is to show concretely how we do this in a very elementary context. So, as I explained, from this formulation, we immediately can construct these iterative schemes. It is not sure that this is useful in the sense we don't know what kind of behavior this iterative scheme has, but if we are in the presence of some conditions, some properties of this operator or mapping or map we discussed yesterday, or transformation, T, or on the setting, on the space where T is defined, then we can obtain some convergence theorems regarding this sequence. And under various assumptions, we can prove in many instances that if T satisfies a certain strong contraction condition, then we have the convergence ensured. So this is our method. We can solve the problem. But as I pointed out in some other presentations, this scheme, which is very simple, very natural, does not work in all situations. So we need more elaborate iterative schemes, especially as we have seen for mappings having satisfying weaker contraction conditions, like the ones I have here, non-expansive, quasi-non-expansive, and so on. In that cases, we need more elaborate iterative scheme. It doesn't matter which kind of iterative scheme. So in this book, you can find this chapter about error analysis, but I speak today in a more elementary way about this. So just a kind of systematization of what I spoke until today. We have this fixed point problem, x equal tx, and what is essential in this with respect to this problem? We need conditions which ensure existence of fixed points. Then in many situations we need to have conditions which ensure also uniqueness of the fixed point, which is the solution of the original problem. Sometimes we are dealing with some topological properties of the set of fixed points in case this set is not a singleton. It consists in many. Hello? Professor Murthy mentioned yesterday other related problems like common fixed point problems, coincidence problems, and point problems, and many other kind of. There is also this class of problems I touched in my presentation: split fixed point problem, split feasibility, and the split common, split coincidence, and many other problems. So in fact we are dealing with mainly with iterative methods for approximating fixed points, and to show some applications of fixed point theorems, to solve functional equations. I have touched this topic. I also have touched this variational inequality problem, but I had no room to discuss about optimization problems, which are very important and which can be also transformed into a fixed point problem, and many iterative schemes used now in optimization are in convex optimization mainly, but not only in convex, also in non-convex optimization are fixed point type schemes. So mainly, as I announced at the beginning, I intend to speak about order of convergence of such fixed point iterative schemes and about the stability of iterative schemes. I would like to discuss this very simple example. We are on, I have three instances for this equation. We have this equation, quintic equation, for which we know we don't have a formula in general to solve it. Now, of course, we can solve it. We take a computer algebra software package and we solve very easily. But we don't consider this. For us, if we denote this left-hand side by f, it is immediately to see that f of 1 is minus 1, that f of 2 is 32 minus 3, so it will be plus 29 is positive, f is continuous, hence for sure we have a solution of this equation in this interval. How to compute this solution? So one way to compute is to transform it in a fixed point problem. I'll show you the difference between various options. So the simplest way, we take this and this will be x to 5 1, and we denote this to be t1 of x, and we look immediately, consider the sequence. Then, to approximate this solution, we start by some x0. It is not important, but we'll start from x0 in 1 over 2. Let's say x0 equal 1.5. So if we start in this way, what happened? Look what happened. T is strictly expanding. We can see this T1 is expanding. What does it mean? T1 of x minus T1 of y is greater than x minus y, and even some constant here. So is, let's say, anti-Lipschitzian. So it's expanding. T1 is also increasing, and it is easy to see that this sequence will go to infinity. So this method is not at all useful for us. So this fixed point problem, because the operator T1 has no appropriate properties to can apply a contraction, let's say type fixed point theorem. Then we go further. The same problem, we can write it, I guess I did by Newton. Let's see to not, okay, this is by Newton. Again, the second fixed point problem. For those familiar with Newton type method, they should know that this iteration function is defined by x minus fx after this one. So t2 of x is this one. The iteration function, and having this function, then our problem is equivalent to this one, and we can see that if we compute this, this will be x to 5 minus x minus 1 over the derivative is 5x4 minus 1, and in the end we get 4x5, all right, plus x minus x, and which is plus 1. That is correct. And in that case, the iterative scheme is this one, which is suggested by this is 4xn to power 5 plus 1 over 5x to 4 minus 1 xn and greater than 0. What happened? This is the so-called Newton method, but I constructed it as a fixed point iterative scheme. And it is known, it is easy to show that this T2 is quasi-contractive. What does it mean, quasi-contractive? I'll show later. Quasi-contractive means that T2 of x minus T2 of y, this is the Banach contraction condition, and quasi means is that T2 of x minus the solution is less than this y minus the solution, its solution, sorry. This is, and we can prove that this scheme, which is the Newton method, converges this time for some starting points x0, but not necessary in 1 over 2. So this xn converges to x star as n tends to infinity, but not for all. I'll have some numerical experiments. I'll show what behave this. So not for all starting points it converges, but for some close enough to our solution I'll show you immediately which is of this equation. And the third way to write this problem is the third fixed point equivalent problem is the following one. Okay, I'll take this. The third fixed point problem can be obtained in the following way. We have this equation, and it is equivalent with this. So this time the equation is equivalent to this problem, fixed point problem, T3 of x, where T3 of x is square. What happened with this map? We can check. This is T3. T3, it's easy to show. T3 of x, I'll keep this notation. It means square radical 5, okay, minus. And what we do, we multiply by the, I don't know how you call in this will be y plus 1 to 4, and here we'll get exactly x minus y. This is positive, we have no any problem, and because this is strictly greater than 1, this will be greater than 2, and then it will be less than that. How many? 5. It will be 1 over 5, 2 to the power 4 over 5. This will be the coefficient, the contraction coefficient. So this is a Banach contraction. And because we know Banach contraction theorems, what does it mean? This sequence xn plus 1 radical of rank will converge to our solution for all x0, and not only in 1 over 2. So this is a difference. What does it mean? We have a nonlinear problem. It should be a differential equation. It should be an integral or a functional equation. By a certain method, we convert it in a fixed point problem. So not any fixed point problem is useful for us. You have seen T1 was not useful because we don't have convergence. T2 was useful because we get convergence, and by performing some numerical test, look, if we start, I did this, our solution is here. Here is somewhere x star, but we start from x0 here, very far from the solution, but we still got the solution after 13 iterations, and using the second method, the second fixed point problem, yes, and using the contraction T3, we get in 5 iterations. So in that case, it doesn't mean that the scheme xn equal xn plus 1 T2 of xn is better than xn plus 1 equal T3 of xn, or the reverse. We cannot say in general, but in this instance, for this particular value, for this particular map, for this particular equation, it happens that the iterative scheme generated by a contraction is converging faster than the iterative scheme corresponding to a quasi-contractive mapping. They are different concepts. So this shows us that in applications, we should try to identify, here is the definition of the quasi-contractive. You can see is exactly like the contraction, Banach contraction, but instead of y, we have a fixed point of this map. So this means we have a contractive. Once more, I want to insist on this. Newton method has rate of convergence 2. But in that case, it converges slower than the Picard iteration. Picard iteration has rate of convergence 1, but it converges in this particular case faster. For this initial value, for this map, it converges faster. So let's have a look on what I did. So we have a functional equation. We want to transform it in a fixed point problem. And if we do this in an appropriate way, then we can use tools coming from fixed point theory. In general, we can get a useful fixed point problem. This problem will be constructive, will be useful for us if the assumptions of, let's say, this equation should be f equals 0, and we transform it into a fixed point problem. If the assumptions on f lead to properties of contractive type, then we can use metrical fixed point theorems to ensure existence and uniqueness. But as we have seen, we could have many equivalent fixed point problems, and so which is the best? This is the problem. Just to stress on what did Picard. So Picard was the first I showed you at the beginning of this course. Picard was the one to note that Lipschitzian property leads to contractive type, to contraction conditions. So this property naturally is converted into contractive type conditions. Also, I mentioned yesterday monotone type properties for an operator which appear in such a problem correspond to contractive type properties. So these are actually our interest. First, how to identify the most convenient fixed point problem corresponding to a given functional equation. We have seen from these three equivalent fixed point problems, the last one is the best, at least from the point of view of this experiment. This conversion, if we can convert appropriately, we'll have a constructive fixed point theorem in the sense that it provides us a method for solving the fixed point problem, which means solving the original nonlinear problem. And the idea is that in concrete applications, we do not get always a contraction like T3. We can get non-expansive condition or quasi-non-expansive and so on. So we need such kind of constructive fixed point theorem. This means fixed point theorems which ensure existence and uniqueness, but for sure this fixed point theorem ensures a method, a constructive method to approximate the solution, the fixed point. This would be our aim always when we face an application. And here is the term I use for constructive fixed point theorem. It comes from a concept in the foundation of mathematics, philosophy of mathematics, if you are familiar. So in mathematics, a constructive proof means that this technique of proof demonstrates the existence of a mathematical object by creating this object, or by providing a method, an algorithm for creating the respective object. In our case, this sequence of successive approximation in many instances it provides a method of constructing the object. This is the object we are looking for, the solution. So this is a constructive and in fixed point theory, of course, the mathematical object is the fixed point, and we are interested to have as much as possible constructive fixed point theorems. Fixed point theorem is logically non-constructive. It ensures only existence of a point, but not provide any method for obtaining. So in this category, we have these famous theorems, but which are very useful in application, Schauder, Tikhonov, and many others, which ensure existence and which are important in problem as Nash equilibrium and so on. There are enough fixed point theorems which are constructive, then we can concentrate, we can focus on this kind of theorems. In my philosophy, a generic constructive fixed point theorem, metrical fixed point theorem, will have the following features. So first, as input, we should have an ambient space, which will be a metric space or a Banach space, any kind of spaces, usually topologic space. As I have shown yesterday, it could be a metric space which is endowed with partial order. So partially ordered Banach spaces, partial ordered metric spaces, and so on. We have as input a mapping possessing some additional properties, but what is the most important, for this map we have a kind of metrical contraction condition. And this category, by this concept we mean Banach contraction, Canaan, Chirich, and so on. And we also mean non-expansiveness condition, quasi-non-expansive, and all conditions in this category. Then, as output of such a constructive fixed point theorem, we should have existence and sometimes uniqueness of the fixed point. We should have a method for approximating the unique fixed point or the fixed points if there are many. And also we should have an error estimate, and also, if possible, rate of convergence, information about rate of convergence, information about stability of the method. As a beautiful model, Banach contraction principle is following all these requirements. And now we are familiar with Banach fixed point theorem. Let's look at it. We have a setting, complete metric space, XD. We have a mapping T. Nothing is required, no additional property. By the way, if you look at the original Banach fixed point theorem, he asked T is continuous. But at that time, when he wrote his dissertation, there were not yet established the concept of continuity for an operator. The continuity has been defined only on real line, so not in a function space. And he said T will be continuous, but we know that any contraction is continuous. And if we have this contraction condition, for sure T is continuous and we don't need to impose. So all items in the output are here present. T has a unique fixed point. We have an iterative scheme, the Picard iteration, which converges to this unique point, and we have this rate of convergence I mentioned before when I presented Banach contraction theorem. And if you remember, I said this is a priori error estimate for n equal I equal 1, and we'll have xn, distance by xn, and x star is less than a over 1 over a. A is the contraction coefficient, d of x0, x1. This is the a priori, and a posteriori we'll have here dxn xn minus 1, which we get by taking I instead of I will set n and so on, but and n1, but I don't write this. This will be a posteriori. I have shown you what is useful having this, and the last condition, this one, shows that the rate of convergence is linear, is 1. This means the Picard iteration has linear convergence, rate of convergence. So I'll speak here about some aspects related to applied iterative schemes. I just mentioned computability, but I'll discuss about rate of convergence of an iterative method and stability of the iterative methods. And I'll consider some context for one-step iterative schemes and for multi-step iterative schemes. In the category of one-step iterative schemes are all with these methods we have seen. I included here Newton method, which consists of the Picard iteration when T, which is called iteration function for Newton method, has this expression I mentioned before. Krasnoselski, Mann, Ishikawa, and so on. There are some authors, they call this, if we start by an x0 in x, and x n plus 1 is like here, xn plus t of yn, lambda, and then yn is, let's say, xn plus theta, this is a two-step iteration scheme. Why? Because we have involved xn plus 1, xn, xn minus 1. So the difference between this is 2. So this is a two-step. But there are some people, in the absence of this term, they call such an iterative scheme is two-step, is not correct. So two-step means this. We have three consecutive iterations. The difference between the greatest one and the smallest one is 2. So this is the difference between n plus 1 minus n minus 1 equals 2. So this is the reason it is a two-step iteration scheme. We have also this kind of multi-step iteration schemes. And this iteration scheme is related to a fixed point by another Serbian mathematician. He gave a generalization of the Banach space of Banach contraction, Banach fixed point theorem, in a very interesting way. He considered T defined on x to the power k to x. K is greater or equal to n and is integer, of course. And he wrote the definition in this way because we are in tk, t of x1, x2, xk is less than alpha 1 distance between x0, x1, alpha 2 distance between x1, x2, and alpha will be distance between xk minus 1, xk, alpha k, and this constant, let's say alpha, is less than 1. Then he proved then T, this if X, D is complete metric space, then has a fixed point, a unique fixed point, in the sense that T of x k times x star is exactly x star. Very nice theorem. And look, if we take k1, what we get? If we are in the situation k is equal 1, we get distance between t of x0, t of x1, we use this notation, is less than alpha 1 distance between x0 and x1, and it is exactly Banach contraction. So in this context, we have this iterative scheme. So k step iterative scheme, which is known to converge to this fixed point. I'll refer, for those interested, in this book I sent you something with it iterative. I don't know exactly what is the title, but you should have this book. Here, this topic is treated in much detail. So let's go further. So we could have one-step iterative schemes. We can have multi-step iterative schemes, but for all, the main numerical features are these ones. So computability, rate of convergence, stability. Computability, you can imagine what is. I don't insist on this concept because it would mean our algorithm is implementable, so we can implement it in a certain software environment, and then we have convergence. This algorithm is finite, is not ambiguous, and is effective. These are the properties, main properties of computability. If you are not familiar with this very interesting topic, which is complexity. Did you hear about complexity theory? Not complex analysis, but complexity theory. It is in computer science. It's about the complexity of an algorithm. This means how complex it is. There are some problems in graph theory, for example. Graph theory. Did you study graph theory at the university? Yes. Okay. In graph theory, there are some famous problems. Traveling salesman problem, for example. This is known to be a non-polynomial hard problem, in the sense that if we have
we have in linear programming.
Oh, in linear programming, of course. Linear programming is also this kind of yes. So this is also this means in fact implementability, and for this problem it is known if we have a graph with, let's say, 6 vertices, and we need to solve the traveling salesman problem, we'll need 6 factorial ways to check which is the optimum. So this is incredible. This is huge number. You can by one method, by the, how is called this method, brute force method. This means to check all possibilities, but there are others. So this is a hard non-polynomial hard problem. Coming back, so this would mean computability. We don't consider this, but some iterative schemes can be easily implemented in a certain computer environment, and so some of them not. So if we have such a scheme, we can implement it. We have an algorithm. It is very natural to answer these questions. How can we find an indicator for one step, single step iterative scheme, which should characterize each rate of convergence, speed of convergence, to have some tools to compare 2 or more iterative schemes, like in our case. We had an iterative scheme corresponding to TT, to T3, how we can compare these two and choose among them which one should be used in application. And this problem leads to a very important concept in numerical analysis, the concept of rate of convergence, which is also called sometimes order of convergence or speed of convergence, and there are many other terms that are used, but this information analytically is obtained by means of this rate of convergence I have shown you before. So if we are in the presence of such a rate of convergence, we had this for contractions. So this we are done. We have the information for this, how we can stop this. And the second one, this formula, if you remember, is about the rate of convergence. So error estimate, rate of convergence, depends how we can obtain. I would speak of some facts I included in this paper from 2016, lot of time, where I discussed on a notion of rate of convergence which is useful in many cases in fixed point theory. And I'll have some information maybe new for you. In this numerical analysis, there exist several concepts of order of convergence. I start by this one, which is the oldest one. We treat it in the general case of a metric space. We have a metric space. We have a sequence xn, which is in general generated by an iterative scheme, and we know it is convergent to some limit x bar, which is the solution of our fixed point problem, solution of our original nonlinear functional equation. And this is the error estimate. If we have such an error estimate where alpha n, it's a sequence of positive real numbers which converges to 0, then this error estimate is very useful. What it says for us? The sequence xn converges to x bar at least as fast as this sequence alpha n of positive numbers converges to 0. There is an old notation for this kind of error estimates with big O. So this means this distance is O of alpha n. This is one order of convergence. This order of convergence comes from these times, so 135 almost years ago by Pringsheim, Abel, Adamar, and so on. They introduced this concept and also the notation. And it comes from the theory of series. I told you about a series of positive terms, and here I can speak in more detail because I presented some parts of this talk in Ghaziabad. He was attending. He's the only one, I suppose, who attended this. But there I could speak just a little bit about this. Here I can afford to speak more. So we have two series of positive terms. They are convergent. They have some s and t respectively. And this, if we have a convergent series, we know that for sure un converges to 0 and Vn converges to 0 as n tends to infinity. And if we have this inequality between the terms of this series, we say that the first series, sum of un, converges more rapidly than Vn, or that the series Vn converges less rapidly than un. This was the concept introduced by these mathematicians, and this inequality implies actually that this the sequence un and this sum of partial the sequence of partial sum we call in the theory of series converge or approaches their limits, which is 0 and s, faster than the sequence Vn and the partial sums Tn converge, approach their limits 0 and t respectively. And this inequality can be, in fact, written in this way. Is exactly what we had. So un minus the limit less than a constant Vn minus each limit, and this is exactly expressing that this has this form, and the sequence alpha n is this one, and this, as I said, this expresses the fact that the sequence xn converges at least as fast as the sequence Vn to their limit. This is one of the most common form of the error estimates we can find in literature for iterative methods. Is not the only one, because there is another one which is usually convenient for Newton type methods. For sure you have studied numerical analysis. So in numerical analysis, we usually have these Newton type methods. They are more elaborate Newton type methods than the Newton method itself. And this rate of convergence has been introduced in this year by Voigt. Voigt is a German name, but he's in USA, in his PhD thesis from 1969, and maybe I've mentioned in a previous talk this beautiful book by Ortega and Reinbold, which is a fundamental monograph on iterative solution of nonlinear equations in one or several variables, which is an old book, but still actual. I don't know about a new edition of this book, but it is extremely nice, and it is useful even if not all methods are fixed point iterative methods in this book, because most of them are of Newton type and many other gradient type, projection type, and algorithms which are not necessarily of this fixed point type. And this rate of convergence is totally different defined. Look, we have a sequence xn which is generated by a certain iterative method, and this sequence converges to the limit x bar, and if we have this relation, so limit of dxn plus 1 x bar over d of xn bar to the power r is a certain finite lambda, then we have the following concept. R is called the rate of convergence of this sequence. Please remember, we had for Banach contraction mapping theorem, we have this rate of convergence. We can do this, and you can see that this is can be written in this way, and this is xn bar xn star to the power 1 less than a, and this is very similar. Okay, we don't know this limit is a or what is it, but this suggests that we have R equal 1 here. So this is the rate of convergence in this sense is 1 for the Picard iteration associated to Banach contractions. And also this number, lambda, has a significance, is termed asymptotic error of the method. If R is 1, as I mentioned, this is linear convergence, and if R is 2, we have quadratic order of convergence, and in case we have R between 1 and 2, we say that the convergence is superlinear. And just to show you the case of this method, Newton method is known for having the rate of convergence 2 under appropriate assumptions on F. So it is necessary that F, in this equation, we are solving the equation Fx equals 0. We have seen this is equivalent to x. This is the fixed point problem equivalent to this one. And this t, this is our t. So for this case, when f is twice continuously differentiable, then the order of convergence is known to be R to be 2. It's not, it's nice proof of this result. What does it mean from a numerical point of view? Because we are discussing today, we are discussing the numerical aspects. This means that the number of exact digits we obtain at each iteration doubles all the time. So let's say at the first iteration we have 1 exact digit. To the second iteration we'll get 2 exact digits. To the third we'll have 3 exact digits, and so on. No, sorry, this is 4. 1 is doubling. So this means that the method is of rate of convergence 2, so quadratic convergence. There are a lot of methods in this family. We have in Romania a strong school on numerical analysis, which is 100 years old, and there are many researchers here. This is another method, Halley method. It assumes that f is 3 times continuously differentiable, and then the rate of convergence in the sense of this concept will be 3, and so on. Now, people are interested to get a big rate of convergence, but all the time, to get a higher rate of convergence, we need stronger assumption on the equation, on the function or on the operator, because all this theory, I'm speaking here on real line, but all this theory is done in Banach spaces. So functional equations in Banach spaces, all this theory about Newton method is translated into Banach spaces setting by Kantorovich almost 100 years ago, less than 100 years ago. So in that paper that I mentioned in another talk, I succeeded to get rate of convergence 1 if f is only continuously differentiable. So you can see rate of convergence 1 corresponds to f is first order continuously differentiable, r is 2 times continuously differentiable, r is 3 times. And it is expected as we increase the the order of the continuous differentiability will get a higher order of convergence. In some context, and I stress on this, f is even not continuous. So that all these methods do not work. And I mention here this problem approached by this mathematician who discovered the demi-contractive mappings. This was the reason he was led to demi-contractive mappings, because his operator f was not even continuous. So he needed some theory for non-continuous functions or mappings for such an equation. And this was the source of defining these demi-contractive mappings. Well, now let's consider some remarks. In the first concept of order of convergence, if you remember, we had involved two sequences. So n and alpha n. And we say that this is a relative rate of convergence. Why relative? Because it relates to the convergence of this alpha n. The second concept, this one, if I change a little bit, I'll have it here. And here it's R. And this order of convergence involves only the sequence, xn, only one. So we say that this is an absolute rate of convergence, an absolute concept of rate of convergence. So we have these two types of rate of convergence. Now, what I want to show you at the end of this talk, first part of my talk, is that we can combine these two concepts. How? We have this rate of convergence number one. I wrote here. If we can compute for alpha n the second concept of rate of convergence, let's say R, so what does it mean? We have for alpha n a limit of alpha n, it's actually, in our case, a sequence of positive numbers. So n plus 1. And its limit, we know it is 0. If we have such a result, then what does it mean? Alpha n has rate of convergence R, and we have this estimate, and how we read this? We read this as the sequence xn converges to x bar at a rate of convergence at least R. So this is different of the previous rate of convergence number one. What about having such kind of rate of convergences? We need we have an iterative scheme. I don't say what kind. We have this sequence. In many instances, you have seen, I gave a rate of convergence for Banach contractions. We can get rate of convergence or error estimates for most contraction type mappings, even for almost contractions. But so we have analytical order of convergence or error estimate, sometimes only error estimate. If we have this, it's all right if we can establish such an analytical. What does it mean analytical? We have a formula. We had this for Banach. This distance is less than a over 1 minus a. Distance of x0. This is an, I guess. Then, because this is the sequence alpha n, which converges to 0. Then we are done. But in practice, we cannot obtain such an estimate for the great majority of the fixed point iterative schemes. We cannot get an estimate of the type 2 either. Or this happens sometimes we have an error estimate of order 2, but is not relevant. And I want to show you this concretely here. This is the simplest example we can have to clear this problem. You can see these sequences, AN and BN. Which is AN? Is 1 over 2. Let's start by 2 to 0. Then it's 1 over 2, 1 over 4, 1 over 8. So 1 over 2 to the power n. And Bn is 1, is 1 over 2, is 1 over 3. Which converges faster? Which one? It's clear, this one converges faster because we approach 0 faster than this one. Look, we now compute this estimate, the order of convergence, and the computation are here. For AN, we have this computation. For Bn, we have this computation. And what does it mean? Both sequences have rate of convergence in the sense of this concept 2 are equal 1. But they exhibit different speed of convergence. This is clear for any child that this will go more rapidly to 0 than this one, which goes slower. What does it mean? It means that this order of convergence is not useful. We cannot compare these simple sequences by this order of convergence number 2. We cannot compare. Our order of convergence is useful, as I mentioned, this one is useful for Newton-type methods because there we can have analytical error estimates, but here it is simply not useful. So we are led to another concept of rate of convergence. If I have time now, we'll stop here for a break. Let's see, it's 11, yes? 15 minutes break, and then I'll continue, okay?
Thank you so much, sir. Such a fantastic talk given by you. And you have talked about the iterative methods. And I can see that you have done lots of research work in your career. And we also want to do like this. But I'm trying to learn such things because we have never done iterative methods before this. And thank you so much once again, sir. And this is the time for a tea break. If you are any questions, so you are, if you have any questions, so you can speak with the expert. Okay, after the tea break. Thank you so much, sir.
Again, welcome you all. The continuous lecture of Professor Brende, error analysis of fixed point iteration procedures, what he discussed in the earlier one also. Please settle down yourself, because we are having some very hectic time today. This is the last and we have to finalize everything on time. So I have some announcement also for you people. All the lectures given by Professor Brende, me, till yesterday, I have uploaded all those. I posted all those in our GIAN WhatsApp group, all, this morning, except few pictures. Mobile pictures are loaded into the GIAN that group, but the photographs which are available in the camera, it will be posted later on, because that needs little bit time to post on the group. Okay, so this is what the announcement is, and after this we have one more lecture, and you will have the lunch, and after the lunch there is one lecture by Professor Veeramani, and it will last till 2:45, and 15 minutes just gap, and we start our validity function. Okay, and in the validity will be fixed for 3 to 4 p.m. only, and as soon as it is 4, Professor Brinde and Mrs. Brinde, they will proceed to Raipur. Okay, so this is what the announcement is. So in the validity function, the participants will receive their certificates also, if time permits. Otherwise, at least the outside participant they will receive, and the local participant, they take the certificate after the validity function. Okay, thank you, and I request Professor Brende to continue his lecture.
Thank you. So continuing this announcement, I have a very special request to you. Especially I'll prefer pictures with ladies. I want to impress my colleagues, because I have a meeting on Monday. So on Monday, next Monday, I have from 8 to 12 lectures, so I have classes. I want to impress my students to show some pictures at the beginning. So please send me by WhatsApp all kind of picture, but I want to make jealous my colleagues. So in the department, I have meeting of the department, I'll show them some pictures, and they will be very jealous about the fact I have picture with so nice ladies. So they will be interested to visit India then. This will be a good advertisement. So please send me any picture with any kind of group involving myself, okay? Then let's go further. So when dealing with iterative schemes in general, with fixed point iterative schemes, we have these difficulties, these drawbacks. So we cannot get analytical estimate of the type 1. We cannot get an analytical estimate of type 2, or we get an estimate of type 2, but it is not relevant, like in this case. So we cannot decide by the concept number 2 that a sequence, an iterative scheme, converges faster than on the other one or not. So we need another kind of order of convergence. This is why I consider this third type of rate of convergence. And I introduce this one. So we have two sequences. AN converges to A, BN converges to B. These are real numbers. We discuss first for real numbers. And if these sequences have this property in the sense that this limit exists, then we have these possibilities. First, if this limit is 0, then we should say that the sequence AN converges faster to A than the sequence BN to B. If L, this limit, is finite and is greater than 0, is not 0, then we'll say that these two sequences have exactly the same rate of convergence. And there is the other case, of course, if L is infinity, is the reverse of case A. This means BN converges faster than EN. But this is implicit. So we denote this fact in the case A in this way, with small o. So AN minus A is a small o of BN. So keep in mind, what does it mean? O of big O of something. And what does it mean? Small o of such sequence. These are different concepts. And I did this for the first time in this paper, which was published in 2004 in this journal, which changed its name. Now it's under a different name. It's something else. Fixed point theory, and in engineering and application, it is again of a journal. It was stopped. The editor was Agarwal, R.P. Agarwal. Hindawi. Then it moves to Springer. Then this journal was stopped to being indexed in Web of Science maybe for 10 years or more, and now it is again. Again, they succeeded. I was an editor at this journal, but I resigned for some personal reasons some 3-4 years ago. And this paper is extremely highly cited because a lot of people found this idea useful when, once again, I repeat this situation. So we cannot have any information of this type, or this situation occurs, we cannot say nothing. So in that case, we can sometimes use this concept. We can apply this concept to several cases. So I'll show you one such situation. For example, we have the rate of convergence of type 2 equal 1, which we have seen is not useful for us to decide about the convergence of these sequences. So I consider the following situation. We have two iterative schemes which generates the sequence xn and yn, and they both converge to a fixed point P of a certain operator T, and we have these error estimates with big O. What does it mean? This means xn minus P is less than C1 alpha n, AN, this is AN, and xyn minus P is less than a constant C2 and times Bn. This is what we know. These sequences, we have seen both sequences tend to 0, because such kind of error estimate is not useful if this right-hand side is not a sequence tending to 0. It's not useful at all. So in that case, if we can prove that this numerical sequence, this is a number, a sequence of numbers, real positive numbers, converges faster than did this sequence of numbers appearing here, then we can say that our sequence xn converges faster than yn. This is a concept I introduced in this paper I mentioned before, and it has been taken into consideration by many mathematicians. Of course, it has some drawbacks also, because these estimates, in order to get good information, and we can infer that we have this conclusion, xn converges faster than yn, then this would be the best error estimate, best estimates. I mean, it is possible to have, let's say, C1 an prime less than C1 an. So in that case, this sequence will be useful. So we should suppose these are the best estimates. So in that case, the information is okay. There were some mathematicians, mainly Romanian, who objected about this concept just a few years ago. They are friends of mine, friends in, you know, what does it mean? So they wrote some negative papers saying that this concept is not correct. It's correct if we have the best estimate here. I wrote a paper as a response to their objection. Their objection were in some sense correct, in fact. So this is about rate of convergence. But as I said, almost all fixed point iterative schemes have linear convergence. So it is possible in some situation to improve this slow convergence, this linear convergence. I show you just a few facts about the research done by one of my PhD students. Juana, it's a female name, so she's a girl, well, she's now married. Juana did this work on accelerating fixed point iterative schemes. So we have a fixed point iterative scheme. It converges slowly in this sense, or in the other two ways I mentioned, concept of rate of convergence number 1, number 2, and so on. And she published a few papers about her research. These are some of her papers about accelerating. And I want to show you just how she did. This is a very natural way, and it is related, strongly related to the average technique, the convex combination technique. Always this method leads to better results. And look, we have this, it is denoted by T of x with parentheses. So we have this fixed point problem. The Picard iteration is this one, and we introduce together this type of acceleration method. Well, we converted this problem of fixed point problem into another fixed point problem. And look, if we define this T lambda in this way, what is this? Here, it's lambda 1. I did not mention they are determined in such a way. It is a linear combination. Actually, it's not a convex, but sometimes it is convex combination. And it is similar to T lambda I considered in the other context when I spoke about enriched mappings. And what is this T lambda of x? We are in that case on the real line to avoid any difficulties. So in that case, we construct this T lambda in this way, and you can see that when we multiply here, this equal x, we'll have x equal T lambda x will be exactly x equal Tx, because all these will disappear when we cancel the identic terms. So we are interested, for example, to find this lambda 1, lambda 2, lambda k. They can be determined in such a way to ensure a rate of convergence in the sense of concept number 2 better than 1, because usually for Picard iteration, I have told you, this kind of iteration has rate of convergence 1. So for these new iterative schemes, PADE type, PADE is the name of a mathematician, will have R greater than 1, sometimes even 2. So this is a method to accelerate a fixed point scheme. There are some other ways, and you can see here this one is PADE type accelerating method of Picard iteration. This here, it's another algorithm, a B method to accelerate iterative schemes. And another concept, Aitken method to accelerate iterative sequences, and some others, I forgot about this. Epsilon algorithm, this is, so at least 3 or 4 methods we have. This is generally necessary to do this when we have slow convergence. If you remember, I presented a result to this split feasibility problem. Not yesterday, the day before yesterday, and there were some numerical experiments for the authors I quoted. They obtain a good approximation after 10,000 iterations. So this is very slow convergence. I don't remember exactly what was the number, but it was something like 50 something or 60 iterations. So we succeeded to get such a good convergence for our algorithm. This means we in fact accelerated, but in a different way, this. So now let's come again to this situation about studying the rate of convergence. We are in the situation we cannot estimate any of these ones, number 1, number 2, number 3. So what can we do in this situation? So we can test the rate of convergence empirically, we say. Empirically means by experiments. This is a Greek word, old Greek word for experiments. And some of these of such kind of results are included even in my book. I included some numerical results obtained by this fixed point software. I didn't know this is a Hewlett-Packard machine. On my computer, my software, this one, fixed point, it was designed by one of my PhD students. This software package allows to study empirically the behavior of a certain iterative scheme. To understand what happened, I'll graph here the simplest situation. So, we have this Picard iteration. I wrote in this way because we are usually using this notation for functions, and here we are working for function. What does it mean that xn is t of xn? This means that the point of coordinates xn plus 1, what happens? It belongs to the graph of t. This is the significance of this iterative. So, if we have here the system of coordinates, Cartesian system of coordinates, x and y, let's say, and we have a function I denote in this way to suggest we are in the same situation. Let's say this is the graph of function, this is y equal t of x. What happens? What does it mean xn? We are here, this is xn, and the fact that xn plus 1 is t of xn, this means this is the point of coordinates xn plus 1. Right? So, we can represent the orbit of this dynamical system, because this is a dynamical system. We start from an initial point and we can draw the trajectory. And the trajectory will be in the following way. I'll show you more examples just to start from an initial value. So, just to tell you that this is a paper describing the implementation and application of this fixed point software written together with my former PhD student, Bozantan Andrei. He's a very bright, he was a very bright person, very strong programmer, extraordinary programmer. He used to be in my department as an assistant professor. I was very happy with him because he was very good, and students enjoyed very much his lectures, and especially tutorials, laboratories in programming. He's an expert. But you know, he left for software industry. He was attracted, I don't know, Google or Microsoft or some such company hired him for maybe 10 times bigger salary than in at the university, and he left. He told me, Professor, please don't be upset on me. This is very important for me. And he moved. Even he moved from Romania somewhere, I don't know in which country, to work for, I guess, for Microsoft. Anyway, it doesn't matter. So he did this nice package, and his thesis is this one. He used this PL homotopy algorithm is used to solve problems when we apply Brouwer fixed point theory. So it's about computing fixed points related to unconstrained optimization problems. Very nice thesis, and he also did some other papers related to implementation of this algorithm. Very difficult problem to implement such an algorithm that I worked 40 years ago. So let's see what is the trajectory of our iteration. So let's say we start by x0, right? Here we go, I'll indicate in this way, this is the first iteration, x0, x1. Okay, to get the next step, I draw the first bisector. And what does it mean? This is the first bisector has the equation y equal x. We are here, this is x0, this is x1, and we go here and we find on the x-axis, this is x1, right? But we now compute t of x1, this will be x1, x2, right? So we are here, we come here, we come here. Now the orbit, how we'll do this? This will be here, this is x2, and we go to the first bisector, and this is also x2. So this is x2, x2 on the x-axis, and what is x3? x3 is t of x2. So this is x3, and so on. Now we continue in this way, again to the first bisector. This will be what? This is x3 measured here. This, okay, my drawing is not accurate, so this will be just equal. Here we have a rectangle. It's not a rectangle. This is exactly x3, and we continue. This is x4, so x3, x4, and again we go to the first bisector. This will be x5, and so on. This is the trajectory of our iteration. Is clear? Because it will be important to understand our numerical experiment. So, such a graph will show how behaves our trajectory. Where is the fixed point of this map? The fixed point is here, at the intersection of y equal x and y equal tx, because this is the fixed point. So this is our fixed point. At least, as we can see here, this fixed point, we don't know what will happen, but the next will be coming here, then it will go there, and it is possible then we'll have no convergence. So this kind of experiments will show us if our algorithm xn plus 1 equal t of xn produces a convergent algorithm or not. In the second step, it also will tell us about the rate of convergence. And look, I'll skip the stability and I'll come back later because I want to show this, and I'll come back to, this is the screen of this fixed point package. It is designed for Picard iteration, Krasnoselsky, Mann, Ishikawa, Prešich 1, Prešich 2, when is this multi-step iterative schemes. Here we introduce the function we work with. You can see is our function I use. So x plus 1 to the power 1 over 5. What we met in this is the experiment was just for this function. And I want to show this. Maybe you will not see from the that position what happens. Look, I cannot magnify this. So this is all we can do. So this is the case x equal T2 of x in our simple problem, elementary problem. So this is the sequence what I intend. So if we start, if you remember, I'm not sure, but the solution is 0, no, it's 1, 7, 1, 6, and something like this. This is x star. Here it is. Here is 0, here is 1, and here is the, I can write here. So, okay, this is the fixed point. And we start with this x0. What happened? You can see. We go there, first bisector, we go here, and what will happen? At the end, it will diverge. It will never go to this fixed point. This is what we can see. If we move this initial starting point, okay, we should note that this function, I don't know, but you for sure have studied how to graph a function. So this function has an asymptote, vertical asymptote here, a vertical asymptote here, and this is the graph. So because of this asymptote, if we start here, we'll never cross the asymptote. So we have to start from something in this region. And then we have chance to get the solution. But anywhere, keep in mind that this Newton method is sensitive to the starting point. Is sensitive to the starting point. If we start in this way, then we'll never reach the solution. But if we start from here, near the fixed point, but we don't know where is the fixed point at the beginning, because this is why we are looking for it. Here is another very nice example. I like this very much, and I explain why. This is one of my favorite examples. I wrote some papers on this nice dynamical system. Is someone studying dynamical systems? For dynamical system, we are interested about stability, and they are chaotic dynamical system, they are deterministic dynamical system. This is an example, very nice, of chaotic dynamical system. What does it mean? The fixed point here we can see. So the problem is, the fixed point problem is 2x plus 2x minus 1. So this means the equation 2x squared plus x minus 1 equals 0. If I am not wrong, the roots are 1 over 2. This one, let's see, 1 over 2. Okay, it's solution, it's a root, and the second one is minus 1, if I'm not wrong. Minus 1, minus 2. Okay, these are the roots. So these are the fixed points. Look, this is minus 1, and here it's, I moved a little bit this. These are the fixed points. Now what happens? This is about the, actually it's about the stability, but I want to illustrate this fixed point package. So we start very close to 1 over 2. 1/2 is a fixed point. And why I like this very much? Because I can prove analytically that this is a chaotic dynamical system. What does it mean? I start from here, and it will never stop. It does not converge. This is a situation when this sequence of approximations will never converge. And what is interesting, we can prove, I proved in some of my papers analytically, neither, you can imagine, here will be a web, never will intersect these trajectories, will never intersect. So it will go continuously, even here where we have big density of the orbits, they will never cross each other. So this is an example of non-stable. I'll go back. But look, if we start with x0 1/2, what will happen? 1/2, it's exactly the fixed point, and from the first iteration we'll get the fixed point. And any value here, if we don't take 1/2, always this will diverge. We have not a convergent sequence. So this is an example. This is this graph is done by this package, this fixed point package, and it draws very nice this. I don't have it. I didn't know you have a Hewlett-Packard machine. On Hewlett-Packard it works, this software, but on my Mac it doesn't work. I don't know why, I could not. And this is fine because we can see how it works. We can see the software did, you just see this movement. You can see how it goes, and so on. If you are patient, you can wait 15 minutes to see how it's drawing the package. Then we magnify this to see how it goes, and we'll see that no orbit will intersect another orbit. This means, because if it will be some intersection, this will be the fixed point, but we do not get. And look, this is very important here. This is the second fixed point. It approaches very close, but it goes again, and we call in fixed point theory in dynamical system, if you are familiar, the dynamical systems, where fixed points are extremely important, are essential, this fixed point P1/2 and P1, P2 minus 1 are repelling fixed points. And we have also the notion of attracting fixed points. Attracting means the orbit will be attracted to this fixed point. But I don't insist. I just wanted to, if someone is interested to have this package is free, I should have on my old machine, I can send you. If you send me a call, I'll send you by mail. It's not big enough. The problem is that sometimes some computers are rejecting it because it's an executable.
Might be not supporting.
Yes, it's not supported for this. My Mac is not supporting it. This is. Yes, Macintosh is not supporting it, and this is why I cannot use. So I go back to the stability problem, which will be my last topic in this talk. So, what is stability? What do you mean by being stable? Is very natural concept in our common life. To be stable means to stay in the same place, to have the same job, to have the same wife or husband. It's also stability. I know some mathematicians which are not stable from this point of view. Okay, this means stable. To be in mathematics, we have this concept in many respects. We have stability of a fixed point. We have stability of the solution of a differential equation. We have many concepts of stability. But I want to speak here about stability of iterative methods, mainly of fixed point iterative methods. And why? When we apply a certain iterative method, we have seen this example of, I mentioned, 10,000 iterations. So you can imagine at each iteration we have a rounding error, we have an approximation, and after 10,000 repetitions, we could have in a certain problem some derivatives we compute approximately, some integral we compute approximately. Sometimes we discretize, we are in an infinite dimensional space. To solve the problem, we consider a finite dimensional subspace and work on this subspace, so we have discretization. All these facts will lead to the following situation. We have this theoretical sequence, xn, but in practice, in our computer, will not have exactly the same sequence because of these rounding errors, numerical approximation. We actually will have a kind of approximate sequence, let's say yn. And normally, it is satisfying the following conditions. Y is 0 is exactly y0 because it's the starting point, but t of x0 is different of x1 a little bit. It's very close but different, and this would be y1. And anyway, this y1 is close enough of t of x0, which is t of y0. So we have this. We have an epsilon 1 small enough, and all these conditions are satisfied. So the new here is the sequence xn, and here is the sequence yn. Because we are in solving a fixed point problem, we know that this sequence converges to the fixed point. I don't know how I denote it here, but suppose it is x. Now the question is, what behavior has this new sequence, the approximate sequence? And of course, in concrete applications, we have some assumptions about this epsilon n, and in the book I mentioned by Ortega and Reinbold, this important book from 1970, this sequence of errors is called round-off errors, from the fact we have this process of rounding at each step. So the problem of the stability in that case for Picard iteration is that one. We have the theoretical sequence of approximation. We have this approximate, and the question is it still converging to, I denote it by P here, sorry. So this will be P, is still converging to our sequence, to our fixed point. This is the problem of stability, provided that some properties are assumed regarding this sequence xn. So epsilon n, sorry. So we can assume xn is a sequence tending to 0, or this assumption, the accumulating errors are finite in the sense that this series is convergent. So this means stability of the Picard iteration. This first question for Banach contraction has been answered by a mathematician called Ostrovsky. You can see even the title is suggesting what is about. So the round-off stability of iteration. He introduced actually first this term of round-off errors. And he proved that the Picard iteration, I'll show you here. So for Picard iteration, in the class of Banach contractions, is stable. This is very important. It's an extremely important result. Engineers are using this property, but they are not aware it exists. They just use Banach contraction theorem for a problem, and the results are good. They work because the iterative scheme is stable, and they get good results. But behind this is this result by Ostrovsky, 1967, very old result and fundamental result. And he established this stability based on this inequality. So he has shown here the alpha is the contraction coefficient. So d tx ty is less than alpha dxy. This was the main inequality he used. Very interesting. You can see here a part of this term is exactly our error estimate. It's our a priori with xn, of course. But this works. So we have these error estimates, and he showed that if epsilon k is a sequence converging to 0, then we have this term converging to 0. Because alpha is less than 1, alpha n is tending to 0. So in conclusion, d of yn p tends to 0 when n tends to infinity, and our sequence, our iterative scheme is satisfying this property provided only xn tends to 0. This is the concept of stability. Now we call Ostrovsky stability. The fixed point group in Cluj they use frequently on other 3 or 4 concepts of stability, which are more sensitive to various situations. Not all iterative schemes are stable. I'll show you what happened later. So Higgs, I mentioned him with this demi-contractive. Higgs, the same Higgs, there was with Kubitschek, and his PhD student Harder, a lady. They did in this period some systematic studies of stability in the sense of Ostrovsky, and they introduced a general definition for stability. I just indicate you, and we read it to be sure all people understand this concept. So their concept is the following one. We have this iterative scheme xn, I did not mention. So we have this xn, which converges to it is known that converge to a fixed point, then we have another sequence yn satisfying this, and we define this sequence of positive numbers epsilon n, and having this sequence, we say that Picard iteration, here is Picard iteration, because it's this one. Picard iteration procedure is T stable or stable with respect to T if we have the implication we had previously in the case of Ostrovsky. Limit of epsilon n is 0, then limit of yn is p. This is their definition, first definition of stability. And it is exactly fitting the approach by Ostrovsky. This was what I presented to you, and why I'm here, because I wanted to show more about stability, what happened with my slides. Okay. Here is what I skipped by error about various other concepts of stability. This is one concept of related to fixed point problems, Ulam-Heyer's stability, and many others. And I told you about stability. I just want to go further and to show you another type of stability. I did not include here the results of Harder. I did not estimate well the time needed for this presentation. So I'll show you what I did. Unfortunately, I don't have on these slides the papers I used to publish. So I introduced another concept of stability, which I called almost stability. There are some others. There are concept of weak stability, and I introduced this concept of almost stability is not related to almost contraction. And what I said, we have exactly the same definition like in Harder. We have a sequence which is not arbitrary, which is an approximate sequence, as I defined before, of the original iterative scheme Xn, in the sense that we have this Yn, Xn, Yn is less than some error or of each step, and then we denote this epsilon and the same exactly like here, and the definition is that this Picard iteration is stable, is almost stable, sorry, if or almost stable with respect to t is important, or t almost stable, maybe I change this, if it's something changed, sum of epsilon n converges implies lim of Yn is P. This is almost stable convergence. It is clear that we can have Yn stable. Let's see. If it is stable, then Yn T stable, T almost stable, sorry, T stable, then Yn is T almost stable. Why? Because we should know from series, if this series is convergent, then we know then Xn tends to 0. So we have the same conclusion. But what is important to tell you, I don't want to forget this, is that you should note that in the definition of stability, the stability is of the iterative scheme. So be careful. Stability refers to the fixed point iterative scheme. But this is important. It involves the map T. So what does it mean? Picard iteration is an iterative scheme. It is stable with respect to Banach contractions, but it is not stable, for example, with respect to other mappings. Let's say non-expansive. Here it's a big consistent literature. And also the problem was studied for Krasnoselsky iteration, for Mann iteration, and there are many papers dealing with this, which classes of mappings ensures the stability of the method. Going to the example I have given you, this one, what does it mean? For this map, for this function, is which one? Is 2x power 2 plus x minus 1. This is, of course, not a contraction. So Picard iteration is not stable with respect to this one, to this map, this function. So stability is not the property of the iterative scheme, but is the property of the iterative scheme in conjunction with the map. So we can have iterative schemes which are stable with respect to some maps, and the problem is that this function is famous in mathematical biology. Is the so-called, is not exactly the logistic. Did you hear about the logistic function, logistic map? Yes. Yes. Is
Machine learning.
okay. This is the logistic map with some transformation, linear transformation I did. So this is why we have here non-stability, because this is a very interesting map. We use this in mathematical models, in population models, and it is known that it has unstable behavior. This dynamical system, which describes the evolution of the population, is stable just for a few values of the parameters. Here we have the parameter which ensure chaotic behavior and non-stability.
In ecology, they use geologists.
I know about logistic map. In many mathematical papers, it is called iterative maps. So this is what I wanted in, let's say, in the large, to tell you about rate of convergence and stability. And I prepared one paper. I have time enough. I copied one of my papers to show you more about the rate of convergence. So keep in mind, in connections to iterative schemes in general, with fixed point iterative schemes, this concept is essential, rate of convergence. Sometimes we don't have any information of analytic, I mean a formula to say something about the rate of convergence. Most of the applications are without such rate of convergence estimates. And I told you when I discussed these applications 2 days before, I'm not happy with papers where they deal with some application, they have an iterative method, they just take one example, one starting point, x0, and they conclude, our algorithm is better than the other algorithm. This cannot be said. Just in this particular case, our method, our algorithm is better than the others one. And then we cannot say in general, this is related to rate of convergence. Stability is very sensitive property of fixed point iterative schemes. Not many papers will find about stability, just theoretical. In my book, you'll find a few facts about stability, but not all information that is now available in literatures. These two concepts are related in some sense, but they are different concepts. They go in some sense hand in hand in the study of application of applied iterative sequences. So I presented you two concepts of rate of convergence, analytical rate of convergence, and a third one combining them. Then I introduced this new concept of rate of convergence for fixed point iterative schemes. Then keep in mind that in most situations, most concrete applications, we are studying empirically the rate of convergence. We just do experiments and we draw the conclusion that our algorithm, our method converges faster or slower, and what it happened. This is typical for mathematician. We have a problem. Let's say split feasibility problem. We take an algorithm and we prove the convergence in theoretically, and we submit paper to a journal. We get after a while the referees, the reports of the referees, and they said, okay, results seem to be correct, proofs seem to be correct, the results seem to be new, and so on. But there is a serious objection. There is no application, numerical experiment. So what to do? we do numerical experiments to answer these objections. And I know as an editor, as a reviewer, what happens. The authors are in a very serious difficulty. So they take an experiment and they take many instances, initial values, and they just select the case when their method is better. But in some other instances, the method is not better. So this is the way, but what is not, nothing is wrong with this approach. The only fact I'm not happy with this is that sometimes they conclude our algorithm is better than the others, and this is not correct. So, as I mentioned some days before, the correct sentence will be, in this situation, in this case, our algorithm behaves better than the others. And then this is correct from all point of view. And this should be the situation, how we manage such a situation. I wanted to speak about another concept of stability. I mentioned just stability, weak stability, and also almost stability, but I did not present it weak stability. I just wanted to challenge you as future work, if you find this concept interesting, this stability is really interesting. There are no, to my best knowledge, there are no any results regarding the convergence of Krasnoselski-Mann iteration for non-expansive mappings, for quasi-non-expansive, and so on. It will be interesting to study. As I know, this cannot be done in the general case. So we need some particular cases, we need some assumptions to get such a conclusion. So this was my presentation about rate of convergence and stability. For some of you, it could be new. It could be not usual. Maybe you did not meet this rate of convergence concept. This I did not finish. So I just want to close by showing you this paper I promised about rate of convergence, which I recommend you for reading. It's useful. No, I took another paper, sorry. This is about what happened. Did you delete the files here?
No,
Where are they?
they are just it.
No, okay, I have it on my, no.
In this. All
No,
files are in this. No, I'll find. I kept in this only.
Okay,
You
but
can open. And today I have sent all the files to our participants.
maybe I was wrong. No, I was wrong. So I did not take the right file. It's about this paper. I'm sorry. I wanted to show you some details about rate of convergence in this paper. I'll just show you. I'm sorry I did not. I had the impression in the morning I put on my memory, so it's just I mentioned here somewhere, and you should write this paper. You'll find this open. Where is it? This one. So this is the paper I wanted to show you to run on it for some other aspects, but the material I included here, it's mainly taken from this paper, and I do suggest you to search for it on a notion of rapidity of convergence used in the study of fixed point iterative methods. This will be the continuation of my, my main part of the present talk. So, let's try to conclude, because this is my last lecture. Please allow me to conclude all things I presented to you. Fixed point theory is extremely large, extremely large. I touched just a few aspects of it, which are familiar to me. But believe me, there are many others I would like to speak on. I didn't do this because I haven't time enough to prepare them. So for me it was easier to prepare this material from what I have. So even yesterday in the evening I realized that I could speak on some other very important aspects of fixed point theory. My intention was now to summarize what I presented. What has been to present some basic facts in metrical fixed point theory, especially related to contraction, Banach contraction, and the class of mappings in this class, where the method we use is Picard iteration. It is enough to have Picard iteration. I am not very happy when I see papers that deal with Krasnoselsky iteration, Mann iteration, and many others in the class of Banach contractions. It doesn't make sense. It doesn't make sense. Why? Because this is a very simple method. We can solve any fixed point problem in the class of contractive mappings, like Banach, Kanan, Chatterjee, Chirich, and so on, almost contraction. We do not need, I have seen tens of papers dealing with such kind of iterative schemes. Okay, they are nice. They show that such kind of methods converge faster than Picard. It is clear they converge faster. There are some papers in that way. Instead of Picard iteration, they use this. Of course, this converges faster because it's 2 times t. So, and if you'll we'll take t3, of course it will converge faster. What happens? We have this sequence. x3 k, x3 k plus 1, x3 k plus 2. So what will happen? When we have t2, what happens? This will be taken into consideration, this not. So our iteration will be x0, x2, x4, and so on. If it's t3, it will take x0, x4, and so on. And normally it will be faster. But this is not a real and interesting result. Yes, it's a subsequence which converges faster. This is one fact. So in my lectures, I wanted to draw your attention to classes of mappings for which Picard iteration suffices. This is the first part of my talk. Then I wanted to show that this method also works in the larger class of almost contraction that I introduced some 21 years ago, and which is a different class of mappings because these mappings are not continuous and the fixed point set is not a singleton. We have more than one fixed point. This was the first part. The second part, I wanted to show you that for some classes of mappings, this was the class of what I call non-expansive type mappings, where we have also a metrical contraction condition. This iteration does not more work, and we need some other methods to approximate the fixed point. Our aim was mainly to discuss these constructive fixed point theorems when we have a method to obtain the fixed point. Once again, topological fixed point theorems are very strong because they ensure the existence of fixed point for single-valued and multi-valued mappings under weaker conditions than this one. We don't ask map to be contraction, to be non-expansive, just to be continuous, and some other assumptions depending on the context. And then that kind of theorems cannot offer a method to approximate the fixed point by their nature, by their assumptions. So I continue with that, showing how most of these results for contractive type mappings, for non-expansive type mappings, can be transposed to multi-fixed points. This was the so-called coupled fixed point, which is a concept coming from applications, from differential equations, mainly for integral equation. And I took this opportunity to speak about the limitations of our theoretical results. So we should be all the time aware that our results have just a limited area of application, and it would be very important. Okay, when we get a new result, we are very happy. Okay, this is new, but we should be aware how large is the area of applications of this result. I've shown you on the result of Bhaskar and Lashmi-Quentin how limited is this theorem. It's very limited area of application. So they introduced this kind of theorems in order to solve differential equations, which are in general difficult. We'll not get really new results by applying such results, as we have shown that for simple elementary problems they cannot be applied. So how to get better results for differential or integral coupled systems of equation. So in the last part, just today, my intention was to draw your attention about the numerical aspects related to using iterative fixed point methods. This is not easy. We should be aware of the fact that any method could converge fast, or could converge slowly. So we should have some information on this rate of convergence. If it is possible, we should be aware of the fact that any fixed point iterative method is linear, has linear rate of convergence. So it is not fast enough. And you should remember also what I presented, that sometimes we can accelerate such kind of methods. This is a very important and nice problem, and there is a rich literature on this. Very important facts. So instead of having 10,000 iteration, if we have some tenth iteration, it's a significant progress. And this would be the third aspect I wanted to point out. So rate of convergence, but last but not least, this concept of stability. So it is important to understand what does it mean stability. In that case, for iterative schemes, this means that we have this orbit, you have seen, we have this orbit, and if you modify at each step a little bit our values, it does not go far away of the solution. This is the the concept of stability. So we need stability for such kind of problems. We need rate of convergence if possible. Otherwise, we'll do experiments and we just look at them. We don't know why we have this behavior or we have this behavior for such a sequence as I shown here. I go back to it. Where is it? No, it is at the end. This drawing of the... Oh, okay, here. So here will be. So we'll have this. If we don't know what it means stability, we don't understand this behavior. Here we have non-stable map. So a Picard iteration is not stable with respect to this very simple function I wrote here somewhere. Tx equal tx squared plus x minus 1. This is a very simple function which provides a dynamical system which is totally chaotic in some situations. So please allow me to say some things. I thank you very much for your interest. It was really a very nice week for me. I enjoyed this course, this nice course Professor Murthy organized. I appreciate your interest. I do hope you'll take some ideas and it will be useful for you what we presented, all our team. I'm sorry I could not attend the other lectures, but I attend the lecture today of Professor Murthy and Professor Veramani. I'm very relaxed now because I had the meeting yesterday at my committee for accreditation. I had to give two reports, but I impressed them. I showed them this, not this poster, the other one. I have shown them the poster and they were really impressed about my activity. I did the reports well. It was very fine. So now I could attend today the meetings. Thank you very much. I'm heartedly thanking you. Please, please do not forget to share with me your pictures, your photos we taken together, okay?
Yeah, actually in GIAN group, you are also the member of the GIAN
Yes,
group.
I am.
So you will continue until and unless we arrive at a concrete position.
Okay.
Concrete position means to publish as a edited book yesterday I
Yes,
said.
but
Yeah.
I am speaking about pics only, from pictures.
Okay. Pictures you can
pictures
post.
with ladies, please send me. I want to make jealous my colleagues.
Okay, yeah. Anyway, you are very smart. So they will post all the photographs, what they have taken, what we have taken, our camera and our cameraman who is coming at 3 o'clock, okay, all those. Before the lunch means once I finish this, I will finish little bit because I am more talking about the concept and some open questions only, okay. So thank you very much, Professor. Your lecture is perfect. See, actually, Sheikh Park always says this. Sheikh Park, whenever he comes to India or anywhere he meets me, so in the audience he always says that this Murthy is my Indian adopted son. This is what for the past almost 25 years he is using this statement only. His wife also. And wherever they come or they meet me, they go to their Indian hearts in Seoul, and from Seoul they bring some sort of food for me because I'm a person who is highly restricted in terms of the taking food. So this is what. So he actually said one thing why I'm saying all those things. So he said one thing that suppose if there is no question from the audience, so you yourself appreciate and then say that yes, since my lecture is perfect, that's why there is no question. So I think Professor Basile Brinde, so lecture, all the lectures are perfect. So I don't think that he has left any scope from the participants to ask. Unless you read more, you don't have the questions. You means you want to ask, it is a different issue, but otherwise really. And what I say is those who are already in the verge of submitting the thesis or willing to now start the PhDs, so better you work on the iteration side. So this is slowly the computational aspects are more, and now these days mathematics without computational aspect, I think now future is a very difficult. That's true. Earlier days we say that algebra means algebra, geometry means geometry, topology means topology. Where the application is your problem. My problem is not to find the application. If you want, you find out. This is what our answer is. Now we cannot give such answers right now. So thank you. Any question from the audience? Oh, Rashmi is having one question.
Sir, as you have shown a diagram. So, sir, if we have a x is equals to 5, then we draw a single line. If we have a y is equals to x, then we draw two x's, x and y. Then we have a x raised to 3, that means we draw x axis, y axis, z axis. 3 roots means this in terms of graphical representation, sir, as he shown in. So that, sir, if we have x raised to 5, then how many axes we have taken and how we can draw?
No, for this one we need only the, we work in plane, but we'll skip some, we'll skip,
Parameters?
I can ask, should we have time enough to, okay?
Please carry on.
So let's see what's happening with these schemes with t to the power 3. This is the question, right? What will happen on the graph?
Yes, sir.
Okay.
Yes.
Look, we have this, and let's have this graph. This will be the first bisector. This is y equal tx, and this is the fixed point. So we start from here. Let's say here is x0. So we go this will be x1.
That will be x2.
This will be x2. This will be x3, and so on. So x1, x1 here, x2 here, and it is clear that we'll take x1 and x2 if we have t square. If we can see we approach the fixed point actually. So what happened is that we skip some intermediate if it's t square. We don't need, we represent on the same graph, but we just keep x1, and if we have t square, if we have t to the power 3, then we'll skip 2. And we'll have only one x0, x3, and this is a subsequence. And this is a subsequence, of course, it will apparently converge faster because we don't take the intermediate. But the rate of convergence is the same, actually. We did not improve the, in this way, we did not improve the convergence. It's exactly the same because we can prove it's just by skipping some, we leave some terms, we don't improve. Is that your question? Okay.
Also, sir, you have drawn trajectories. So why drawn their trajectories? And what kind of that? Orthogonal trajectories or something else, sir?
You mean this? This one?
Yes, sir. And there is intersection points, then we have fixed points. So why you have drawn these trajectories?
here.
Kind of. Yes, sir.
Here, as I explained, no any trajectory will intersect the other one.
sir.
Because if it will be some intersection, then we'll get the fixed point. Look, if we have, let's say, t of xn equal t of xn plus 1, then we have exactly reached the fixed point. So no one, once again, I insist on this. I proved analytically, this is not empirical proof, because this is why I consider this example. I work here with cosinus, with sinus, which are known how they behave, and I can prove analytically that these trajectories is just to understand that they will go always. This is the density of the real set of real numbers. Should we understand this beautiful nature of the real numbers? This is a dense set. Always we can find an infinity of real numbers or rational numbers in any neighborhood of a given. So this means that we have exactly the same situation. We don't have trajectories intersecting.
Yes, sir.
For this example, look, for this example, here it is clear we have convergence. It goes to this fixed point.
Yes, sir.
All right?
Yes, sir. Thank you, sir.
Okay.
Thank you, Rashmi, and thanks, Professor. Any question? If no, okay, we applause. You have question? Okay. Last question of this session.
Professor, you just said if the trajectory will coincident, then there will be a fixed point.
Yes.
What about 1 minus x, if we take any point other than 1 by 2?
1 minus x, you can do simply this one. This will be oscillatory.
But the trajectory will coincide.
No. Let's see. You say 1 minus x, right? In that case, one minus x is this one, right? It's not this one. Sorry. It's yes. This is minus. This is minus x. So it will be for x1 it will be 0, and for x0 it will be 1. So this is the graph of y1 minus x, and this is the first bisector. It doesn't work. Okay, I'll take this. So this is the first bisector. I'll draw in this way. And we start for any, the fixed point is here, and obviously is 1 over 2, because this means x 1 over 2, right? And we start, let's say here, x0. We go here on the graph, right? Then we go on the first bisector. If my draw is good, we'll have exactly what happens. So this is this. Then we go, where are you? This is first bisector. We go on the graph. It will be a little bit here, and then we'll come here. Normally, I did not draw correctly. Again, if it is, so it will repeat. So it is doing this.
Yes, sir. It will coincide now. The trajectory will coincide.
It's never going to the fixed point. This is the point. So it is x0, y minus 60, x0, and so on. Exactly what I said. So this is the graph representation of the oscillatory behavior of this for this map of the Picard iteration.
Okay.
Okay.
Thank you, Professor.
Okay, now it's my pleasure to be in the position of a moderator and not a speaker, so I would invite Professor Murthy to present his lecture, Historical Results and Their Consequences After Banach, Canaan, Young, and Part 2. Thank you for this interesting topic. I am really interested.
Thank you, Professor. Top. PPM top. Fundamental. Okay. Thanks, Professor. Basil Brende. Actually, yesterday I have given some information and the interesting some fundamental and historical results in fixed point theory and applications, that how the fixed point theory evolved after Stephen Banach, Canaan and Young. So only few things discussed yesterday, and as I promised yesterday, I will be just introducing about, because we have only very less time, 20 minutes time. So I will just discuss about very interesting questions what I find for the past several years. And as I said, I am working for such problems 20 years and unable to find the examples. So let us see what exactly I mean to say. So yeah, there are, yesterday I was talking about, there are two norms. If I say this as a Banach norm and the second one as a Frechet norm. So let us see what is a Banach norm. So this is the Banach norm, that norm of x is 0 if and only if this is very common. First, second and third condition, this you know very well, okay. And X is a linear space, as I said yesterday also, we are talking about the linear space, and the Banach norm is discussed in this manner. The second one is the Frechet norm, or we call it as a F norm. So some conditions we are going to relax, okay. So condition 1 and condition 2 is taken, and we are relaxing the condition 3 by the underwritten condition to call it as F norm, okay. This is the condition 3. Now we say what exactly the two norm linear space. This is 2 TWO2. See, there are some other works also the people have done. This is the 2 norm linear space. This is also Anderson has done, Cho has done, Cho's supervisor, he has also done. So lot of works done in this area in the context of the fixed point theory. So this is the 2 norm, and they pick both of them, okay. B norm they call it as the N1 norm, and F norm they call it as the N2 norm. and the linear space X is cubed with both norms n1 and n2. Okay? Let us see the next. These are some important definitions. So, related to n1 and n2, so when you can call the norm n1 and norm n2, so which is the weaker one or non-weaker one. So, normally in topology we have the weak topologies. Okay? So, here also we have the norm n1 and n2, and we define in this manner that when n2 norm is stronger than the n1 norm. Vice versa also you can define. Now, this linear space X is cubed with these two norms n1 and n2, and we are defining a sequence xn in the linear space X, and they call it as a gamma convergent sequence. And when it is a gamma convergent sequence, if it satisfies this condition, the supremum of n1x, okay, is less than infinity, and limit of n2 xn minus x is equals to 0. So, naturally when you talk about the gamma convergence, so we talk about the gamma Cauchy sequence also. So, this is the gamma Cauchy sequence in this space x, n1, n2. So, this is this triplet. So, these are some more fundamental properties using the B norm and F norm. And now I am coming to the main point, that the set Xs is defined. So, how it is defined? The element of capital X where the norm n1 is a Banach norm, is less than 1, and the distance is defined with respect to the Frechet norm, n2 norm. The distance of xy is equals to n2 x minus y, means norm of, even you can say norm of x minus y, because I am it's a notation for the Frechet norm. So, we have written n2 x minus y, okay, for all x y belongs to xs. So, this xs we call it as a Sachs set. This axis we call it as a Sachs set. Let us see the next definition. Now we have the Sachs set, okay, and this Sachs set, when this Sachs set is said to be complete, we have the Cauchy sequence, we call it as a gamma Cauchy sequence. We have a convergent sequence, we called it as a gamma convergent sequence. Okay. So, same, every Cauchy sequence is a convergent sequence. Okay. So, in that case what happen? If you can define every Cauchy sequence is a convergent sequence in the Sachs set, then the Sachs set is said to be the Sachs space. So, this is the Sachs space, and we have defined the Sachs space in this manner. Now, we are using this lemma actually. My issue is, as yesterday I said, my issue is very clear. This is a lemma, the famous lemma, as I said, given by Patak, P-A-T-A-K. Okay. So, he has given this lemma, and what the lemma says, if this is a Sachs space, okay, with two norms n1 and n2, Banach and Frechet norm. So, you can see here x n1 is a Banach space, and what happened? n1 is weaker than n2. The second one is x n2 is a Frechet space, n2 is weaker than n1 on x, and it is a conventional notation. So, we used to define this x SD is a Sachs space, okay, and we say that this n1, the norm n1 is equivalent to norm n2. We say this. We are using this lemma. So you can see you can understand the proof also. So like we introduce this weak contraction, you know Billy Rhodes, Professor Billy Rhodes, he introduced the weak contraction condition in 2000, and I am the person who is witness for him for this weak contraction, because he introduced this in WCNA 2000, Catania University. So as I said, we were there for around 10 days. So one of the day he introduced this condition, and in that condition he was not using this one, he was using something like this. The distance between Tx, Ty is less than or equal to the distance between xy minus of some, you can say here some alpha or something here, okay, some function or some alpha I can say, and here the distance between xy, means this is the negative part. This he used in his theorem, and later on these are the developments that of course we introduce phi, and as I said, in my lifetime few theorems are there, they are very limited, even not more than 10, and their impact is very high on me, and one of them is Boyd and Wong, this theorem also. So I studied first time about phi after Banach when I have gone through the Boyd and Wong's paper. Of course the Boyd and Wong also use the concept of other researchers' work, but I have seen first time there. So here Professor Billy Rhodes used the same, phi is a continuous function, but you can see that in many results of the metric fixed point theory, phi is now these days is a upper semi continuous functions in place of the continuous function, which is a weaker condition than continuous. And in place of the one parameter, they have used more than one parameter. In place of the linearity, they have used the second degree, third degree, and some people use the nth degree also. So this is the condition we have used, and fine, this is we call it as a altering distance function, and this altering distance function introduced by KPR Shastri, who is a professor of Andhra University, Visakhapatnam. So he introduced this, and this appeared in Yokohama Journal of Mathematics. It's a very around I think 1982-86 that time. Later on Silvestro Sesha and MS Khan, they have used this condition, this phi function condition, altering distance function condition, and proved some fixed point theorems, and that paper published in Journal of Australian Mathematical Society. This is around 1984 I think, 84 or 86. So this is the condition we used, and some functions introduced. I think those who are the using this contraction type, they can understand this. This is very famous. These are some particular cases you can see here, and especially Fisher used such kind of conditions, and some results I don't, Shahzad used or someone else used. I am not recollecting the name of the mathematician. He is from some UAE, and he used so many this kind of implicit functions, and by using the implicit functions they have proved several results. Velur Popa, he did, I think he is from Yugoslavia? No, from Romania. Okay. I know him personally. Oh, you know him, right. His papers are very short, writing many papers. One theorem 2 theorem, 1.5 theorem and finishing the paper. That is his style, and Professor Pathak wrote so many papers with Velur Papa. So these are the somewhat that kind of results you can see. So actually where exactly the problem comes that I am interested to discuss with you. This is what the method to construct a Cauchy sequence, and using the completeness of the space, or if the space is my range is closed subspace of even a non-complete metric space, even though we are in a position to prove. Yeah, so I think the proof I have not given. Let me check whether proof is given or not. These are all the corollaries I am discussed about. Yeah. So what happened actually, fine, when I am using the Sachs sets, so I am using the N1 norm and N2 norm both, right. So separately, independently I am using N1 and N2 norm. Difficulty comes when I am separating them and trying to correlate, but failing to do so. So can we have any example to say that yes, I have the Banach norm, I have a Frechet norm, and using these two norms we have the convergent sequence, and this convergent sequence where it converges is a fixed point of the transformation or the mapping. This is the difficulty. So my question is whether we can relax this lemma and prove the theorem in Sachs spaces. Because of this difficulty, this space has not gained that much popularity as other spaces are gaining. Of course, we know that metric space, like metric space there is no space, like nonlinear space there is no space. In a hyperplane if you want to go, then you have the Hilbert space. But there are some problems still persist. One more question. This is one question. The second one is, yesterday I was discussing about the Gregus type map. The Gregus type map is very simple. If T is a transformation from x to itself, this Tx Ty is less than or equals to alpha times of distance of xy plus beta times of distance of xty plus yta xtx yty, okay, and gamma times of, if you say, okay, actually the total sum of this equals to 1, the sum of the constants are equals to 1. Of course, in the beta and gamma you have to write 2 times because averaging once again. Whereas if you apply the Banach contraction condition, it will not be valid, because you have to presume, like he was discussing, many results of Charik. So even we use the same, all the 5 possible combinations he has taken, alpha times of maximum of distance of xy and other 4 combinations. But here alpha should be less than 1. In this case, if you follow the Banach pattern, then you have to say alpha plus 2 beta plus 2 gamma should be less than 1. Then only, like professor was talking about, the construction of the sequence plus some constant he was talking, some series he was talking about, plus some series. So in other way we can say is some error actually, plus something means. And in his case he was saying that when n tends to, because it is sigma some I equal to 1 to n, if n tends to infinity, this is deemed to be 0, the right part, and he has alpha to the power n by 1 minus of alpha, and alpha is less than 1 when n is greater than n tends to infinity. So alpha to the power tends to 0. So ultimately your denominator is not 0 because alpha is less than 1. So 1 minus alpha is greater than 0. So in that case the first term is also 0, and he has proved, he has the results, the second error part, that is also 0. Then only xn converges to some a or x, whatever the fixed point, right. So our problem is, what we have done is, we have done the same thing in non-linear space. Convexity we used, and we use like this. This is alpha times of norm of x minus y to the power p, okay, plus beta times of maximum of this norm of x minus tx to the power p, norm of y minus ty to the power p. This is, and this looks like non-expansive. Alpha plus beta equal to 1 is 1, is not less than 1. If it is less than 1, I have no issue. Or you can replace beta equals to 1 minus alpha, linear combination, okay. So if this is the condition, your iteration is the Picard's iteration. Xn plus 1 is equals to Txn, okay. This is the iteration. So once again the same issue. We have a feeling, we get intuitions, understanding that the sequence is monotonically decreasing. But the question comes, how you are going to show that is a Cauchy sequence? That's the issue. The open question is given. This paper published in 1995 in Glasnik Mathematica, Gregus type maps, and open question is given at the end of the paper. And as I said, this paper took almost 2.5 years to publish. Out of the 2.5 years, it took almost, I think, more than 2 years for revising the paper. They are not satisfying with the evidence, now they are rejecting the paper. Every time I think the editor is interested to publish the paper, and he was needing the paper to be improved. And finally, I have not succeeded to show that, and as I said yesterday, finally what I have done? I have done only one thing, and that thing is I replace, finally I fed up and I introduce the control function, and this control function is upper semi continuous, this one. So that way this problem resolved. But once the open question is, under what condition, when you remove phi from the right hand side of this contraction, so your sequence converges. Still an open question, and I think this problem can be solved by those who are working on the iteration side, and particularly Professor Brinde type people, they can understand well, because it's a looks like a non-expensive type map. Yes, that's why. Yes, that's why. And here power is p, so normal inequalities won't work, because triangle inequality issue is there. Lot of problem. How to overcome Abel's lemma? Okay. So these are some issues I faced for the past 20 years, not getting the answer. So I think the time's up. So let me close my lecture. Thanks to everyone listening very carefully. Thank you.
Thank you, Professor Murthy. Very interesting things and open problems. I just wanted to say it exactly. Gray-Gush type fixed point theorems are related to non-expensive type mappings.
Yes.
Because they are actually, most of them are quasi non-expensive. So this could be a solution to take the same tools like in the case of enriched non-expensive, so not Picard iteration, but Krasnoselsky type iteration.
Yeah, yeah.
So thank you. Now it's time for lunch. Thank you again.
This is the time for lunch, and we all assemble here at 2 p.m. here. So before that, I think before we go for lunch, please come to the main gate, and we have at least one photograph, and if time permits, we go for the another photograph later on. Please come.
session is going to start after lunch session. And in this session, Professor P. Veeramani, Professor, IIT Madras, he will speak about the role of best proximity point theorems in metric fixed point theory. He will speak about this. I think so many lectures he has given for the past 4 days. Today is the last day and this is the last lecture also. So listen very carefully, think about what he said, on what he is working. If you are really willing to do some good research work, you can view the videos, and these videos are streaming forever on the web. So after, I will try to ask the organizer of the videography, Mr. Rajesh, okay? So he will send us a single link for all the videos, and I will forward all the videos to your WhatsApp group, and you can save that link and you can visualize. Or even in Google, you can do the Google, and in Google, if you put this title of the GIAN program at Bilaspur GGV, I think easily you can get. Okay? So once again, thanks a lot for your very nice and calm present over here, and Professor's arrival, and he will be departing tomorrow morning. We are very much indebted to you, sir. So you have done tremendous work here, and many thanks. And I once again welcome you for this session. Please carry on, sir. Thank you.
It is always very nice of Professor Murthy to talk something, more affectionately, maybe. Okay, again thanks. Let us start. First, maybe 10-15 minutes, something which I wanted to give. Especially we were all discussing about contraction, result related to contraction, and what is non-expansive map. We did some result even for continuous, and then Kakutani fixed point theorem. So at least using proper fixed point theorem, one can prove those results. So now again a simple application of Banach contraction theorem to non-expansive map. We have seen that if it is a closed, even a compact set, the domain is instead of convex connected. You have seen that. So like this, the unit sphere in R2, x mean order pair x1, x2, we discussed already, will not spend time. Norm x equal to 1, then Tx equal to norm x, T from the unit sphere to itself. In fact, it is norm of Tx equal minus Ty, distance between Tx, Ty equal to distance between x and y, isometry. Still there is no fixed point, there is no x in S1, the sphere, so that Tx equal to x mean x should be equal to minus x, that means 2x is 0, so that is possible only when x is 0 is not in the domain. So now we will see how we are going to use a Banach contraction theorem. Here note that, that's what we have seen, that motivation to proper fixed point theorem, that this gives a motivation to go for convexity. Though circle is connected but not a convex set. So that's why proper fixed point theorem we need convexity, not just compact will do. Compact, in addition to compact, if you assume connected subset also not sufficient. So here we assume that X a Banach space, capital K non-empty, closed. See whether we are using each and every thing. Closed, we need bounded, convex, subset of our Banach space X, T from K to K, non-expansive map. Non-expansive, note that K closed bounded convex subset, K from K to K non-expansive, then we will not able to find a fixed point, that then there need not exist an X say that Tx equal to X are all what will happen if it is a finite dimensional nonlinear space, then closed bounded imply compact, then our set will become compact convex, and T from K to K non-expansive, in particular it is continuous map. T is a continuous map from a compact convex subset of a Banach space. T from K to K, even continuous Hapesian, it will have a fixed point. Okay? But here what is? Compact is not there. There is very strong condition. That's what we stated. In place of compact, if it is a compact with respect to weak topology, K weakly compact convex, T from K to K non-expansive, we need an additional structure called normal structure that we discussed in short. Then it will have a fixed point. That's if I will indicate the outline. So an simple example of, so then this will fill up the gap. Now consider, are you familiar with what is C naught? C naught is each element is a sequence, we will assume sequence of real number. C naught, C0 is for all real sequences converges to 0. So we will assume that set of all x equal to xn, sequence of real number I am not writing, so is that okay, if you want xn belongs to R, xn converges to 0. So then what is the norm here? Norm is, because it is a convergent sequence, any element here mean it is a x in C naught mean x equal to some xn, xn converges to 0. Every convergent sequence is a bounded sequence, then it will have upper bound, lower bound, so supremum will exist. Then you can verify that it is a Banach space, okay, it is a standard thing, it is a Banach space. Now take a closed bounded convex subset of, even take the unit ball. Here it is, K is set of all x in C naught, x in xn, so that norm x is less than or equal to 1. I mean this is closed, this is nothing but our notation mean this is like distance between, that is x and 0 is less than or equal to 1. This is nothing but the closed ball, center at 0 vector and radius 1, which is closed, bounded, convex. Okay, we will define T from this k to k, T from k to k as T of an element here mean it is a sequence x1, x2, x3 dot dot. The image is first thing will assume some non-zero element. So if you want take any element, not suppose it is say 1, then x1, x2, x3 dot dot. Translation, shift, we call it shift. I mean we are just shifting from here the first element, not 0, 1, x1, x2, x3. Okay, now what is norm of Tx minus Ty? Tx mean norm of 1 x1, x2, x3 minus 1 y1, y2, y3 like that. Then supreme norm of this, norm is supremum of modulus of first term minus second term 0. Then mod x1 minus y1, mod x2 minus y2, that is nothing but mod xn minus yn, that is nothing but norm of same thing as distance between x and y, norm x minus y, that is norm of Tx minus Ty equal to norm x minus y. It is an isometry. That means in particular norm of Tx minus Ty less than or equal to norm of x minus y, and the set is closed, bounded, convex set. Whether it has a fixed point, what will happen? Suppose there exists x means sequence xn such that Tx equal to, we will see what will happen. Tx equal to what? X, fixed point mean, but what is x? X is x1, x2, x3, but what is Tx? 1 x1, x2, x3. So these both are equal component wise. X1 equal to 1. Here x1 1, x2 equal to x1. That means x2 also, x2 equal to x1, x1 equal to 1. So then x2 like that. So you will get 1 1 1 1 dot. This is possible only when x equal to 1 1 1. But where we are, our space is, so this is a sequence, constant sequence, 1 comma 1 comma 1 comma 1 dot dot. So this converges to, we don't bother whether it converges or not, it does not converge to 0. Don't say it converges to 1, it does not converges to C0, that's why it is not in C0. So that means it cannot be in K, K is subset of C0. So we have a nice closed, bounded, convex subset of a Banach space, T from K to K, in fact isometry, norm of Tx minus Ty equal to norm x minus y, mean it is an isometry, still it need not have a fixed point. We cannot expect a fixed point, that's why we need additional condition. So motivated by this, by a simple application of Banach contraction theorem. So then what this says that this is for any Banach space, X Banach space, K closed, bounded, convex subset of the Banach space, T from K to K non-expansive, that is same thing, that is norm of Tx minus Ty less than or equal to norm x minus y for all xy in the domain. Then we cannot get a, that we have seen example, we cannot expect a point x such that Tx equal to x, but we can almost, that we call it approximating fixed point sequence. Then there exists a sequence xn in K such that norm of xn minus txn or txn minus xn. Txn minus xn, it is almost after, that means it converges to, it is approximating, like all numerical thing, approximating means it approaches to 0, that is it approaches to 0 as n tends to infinity. Anyhow, because of time I will give the proof quickly. This is symbol fix x naught belongs to K. For each natural number n, for each n belongs to n, define Tn from K to K as, here the role of convexity comes. Tn of T suffix n of x equal to 1 minus 1 by n. See, x is in K, that means Tx is defined, okay. Tx is again in K because the map is self map. X is in K means Tx also in K. Then plus 1 by n, that fixed element x naught. X naught is where? X naught is in K, Tx is in K. This is our like alpha time Tx plus 1 minus alpha. So like here alpha if we take 1 by n. This is convex combination of, see this sum 1 minus n plus 1 by n is 1. So this is convex combination of Tx and x naught. Hence it belongs to where? Belongs to K. That means this Tn, hence this Tn is a map from K to K. That is T1, it is a map from K to K. What type of map? See, quickly it is easy to see that. Again calculation I will leave it as an exercise because time is not there. Tn, for each natural number n we have one map, that map is Tn. Tn of x minus Tn of y, in fact see, this is nothing but Tn of x means what? This. Tn of y means 1 minus 1 by n times y x plus, this is fixed, 1 by n times x naught. So what will be Tnx minus Tny? This 1 by x naught minus this will get cancelled. This will be less than or equal to 1 minus 1 by n, just to write immediate, times norm x minus y. This is our K. K, or you can call it Kn, contractive. So Tn is a what type of map? K to K is a contraction map. What is K? Closed subset of a Banach space. Closed subset of a complete metric space is complete. So now forget about convexity all. So Tn will have a fixed point. Hence there exists xn, say that, so okay, we will get some Tn equal to xn. This is for every n. Okay. Now what is our rule? We want now see that now norm of xn minus txn. What is xn? For each n, one function Tn, that is a contraction, then it has a unique fixed point. Forget now, unique doesn't matter. It has a fixed point. Xn, so the Tn xn equal to xn. That xn, that means what this is? Tn xn. because Tn(xn) equal to xn minus Txn. Okay. Our again but what is Tn(xn)? By definition, Tn(xn), come here, Tn(xn) is 1 minus 1 by n T of that element instead of x, xn, Txn plus 1 by n x naught, that x naught is fixed, minus Txn, correct? So, then see here this 1 by n xn, this we can write, this Txn, how we can write? 1 equal to 1 minus 1 by n plus 1 by n. So, this will become into Txn, that means Txn will become 1 minus 1 by n Txn plus 1 by n Txn, so this will get cancelled. Then triangle inequality will be getting, this is less than or equal to 1 by n xn minus x naught. I have written correctly, sorry, Txn. This 1 plus 1 by n time Txn is there, plus 1 by n time Txn, sorry, n we have taken out, this again, here the minus, here minus will come, then that way this 1 by n time norm of Txn minus x naught will come, all these are all in the set K, Txn is in K, x naught is in K, K is now not at use, with fact bounded we have not used. So then this will be less than or equal to this work out, diameter of the set K, this tends to 0 because diameter is finite. So 0 less than or, that means we get a sequence xn such that norm of xn minus Txn tends to 0. That means we get an approximating fixed point sequence. See, that means if you want a fixed point, we may not get exactly equal to, your error is say 0.0001. Then we can find a stage n naught such that norm of x n naught minus Tx n naught is less than that 0.001. Almost this x n naught will be an approximating fixed point type. I mean, depends upon our need we can use. When there is no fixed point, this is a known result. You can read like Comte and Kirk, any book in fixed point theory. In fact, yesterday we were discussing with some of you, told anywhere full convexity we are using. In fact, what we have used is, we have fixed a point x naught, even if it is like this. Take any point x, x and this is there. That convexity only, that you check whether you need, but that is nothing new. I mean, essentially same result, but check properly whether it works. Such concept is called star shaped set. Mainly in convex analysis, I mean complex analysis you come across. Jones lemma proof I will not have time. What is that we have seen? K, even that's what for us, closed, bounded, convex set, T from K to K, non-expansive, implies the Rx is x in K such that Tx equal to x. You can use Jones lemma to get a set which is invariant. K is invariant set, T of K is subset of K. We can get a closed, bounded convex set, say F, which is invariant, that means T of F is subset of F. This is minimal such set, then that is non-empty. So using Jones lemma we can get, then we will prove that that set F is singleton. For that you need parallelogram law or what is using normal structure. The set has more than one element means it is a non-diametral point. Then using that concept, because that alone it will take at least 20 minutes. That is standard result. There are, as I told, there are many open problems. If the space X is a reflexive Banach space, the canonical embedding is onto. Then K closed bounded convex set, then it is compact with respect to the weak topology, meaning is the unit ball is compact with respect to weak topology. Every closed, non-empty closed bounded convex set is compact with respect to weak topology. T non-expansive, then we do not know whether it has a fixed point or not. I mean, neither we know an example nor we can prove it. There are even whether we can renorm L2, some renorm will have fixed point, even L2. Not every renorm of L2 we do not know. Even there are many non-trivial interesting open problem. Now just brief introduction to the title. Okay. Again to, because all of you are more interested in look like contraction map. Okay. First, my first set is capital A, set of all the vertical y axis. What is y axis? Set of all x, here take any point here, order pair 0, x. X belongs to where? R. X is any real number. Set up all order pair x, 0, x such that x is in R. Okay. Can you give a map T from the set A to A such that it is a contraction map? We can give or not. Can you give a map? T from A to A. See, suppose T is a map from R to R. Can you give a simple map such that T is a contraction? Tx equal to, suppose 0 less than or equal to k less than 1. Then Tx equal to kx will be a contraction map. Mod Tx minus Ty equal to modulus of kx minus ky. K times mod x minus y, k is strictly less than 1, less than or less than mean equal to mean you can write equal to k mean less than or equal to k times mod x minus y also true. So they symbol. So we can give any non-trivial example also. Okay, we can give a contraction map. See, instead of here what we can write? Define T from as T of only thing, it is just nothing, it is R only. Instead of first coordinate dummy, then we can take alpha x or 0 less than 1. Alpha or k doesn't matter, just okay, that is not a problem. Okay, now I draw another vertical line. Anywhere you can start, just for take this point as 1, x is 1, y is 0. This is vertical again. Oh sorry, it is straight line, not curve. So it is a vertical line starting from, sorry, okay, because, okay, this first, okay, this is 1, 0. This is our set B. What is capital B? Each element here is the same thing A. Only thing we have, just from here we have moved same object we have moved, translation. So what is set of all 1 comma x, y doesn't matter, x belongs to R2, so that x is in R. Okay. Now, is it possible to define a map, another map, call it S, from A to B, such that norm in distance R2 here, we are in R2. Distance between x mean what is any element in, now any element here in the set A is 1 0 comma x minus another element 0 comma y. This is less than or equal to, again like contraction. Is it possible? Again essentially that's why it is almost like same map. There is no difference between, see now you take any element here 0 comma x, we want that should be here. Any element in the second set B mean the first coordinate is 1, second coordinate any real number, we want contraction. So this is alpha x, that is we are defining S of 0 comma x equal to 1 comma alpha x. Alpha is fixed, 0 less than or equal to alpha, strictly less than 1. This is clear? Okay. Now what can you say about what is norm of S of 0 comma x, one element, if you want one more, minus S of 0 comma y. So this is by definition norm of S of 0 comma x mean 1 comma alpha x, sorry, image minus 1 comma alpha y. So what is the norm? Root of or L1, this get cancelled, alpha time alpha x squared, so that means what? Alpha time x minus y. So we will have alpha that less than or equal to alpha time norm x minus y will have.
By applying false level.
No, false, direct here. Okay, by the definition. So, yeah, now we have defined S of 0 here, 1 comma alpha x, yeah.
This S is the open sphere.
No, S is a map
Okay, map.
from the set A to the set B. This vertical line to another vertical line, this is vertical line passing through 0 0, this is 1 comma 0. Can you get a fixed point? Now A is this vertical line, capital B another parallel vertical line. Okay, can you get a point x, say that any point here equal to 0 comma x, 0 comma x is here, S of that will be vertical line. It is geometrically it is trivial, there is no such a nice map, we cannot get a fixed point. But for the map T, do you have a fixed point? Okay, see here, but that's what is the distance this point, okay, again due to time 0 comma 0. What is the image of 0 comma 0? 0 comma 0 goes to 1 comma alpha times 0, that is S of 0 0 equal to 1 comma 0, and what is S of 0 0 and 0 0, S of 0 is, what is this distance? 1. That is same as distance between these two sets equal to distance between A comma B equal to 1. That means, yes, yeah, 2-3 minutes I'll take, 5 minutes. Okay, we can get at least S there is an element in the domain A that naturally we cannot expect a fixed point, but there is a point, in this case 0 0, such that distance between S of 0 0 and 0 0 equal to distance between the set A and B. This is a trivial thing, but it has, I mean, why want to give this is just a simple motivation to consider map, two disjoint map like two vertical line. So then whether we can find a x, say the distance between x and the image equal to distance between the set A and B. In particular, B equal to A, Tx equal to x or Sx equal to x. So now can be, is it possible to go to a general Banach space? What will happen? Suppose, can we imitate this example to a Banach space? You keep this in mind, X is Banach space, okay. A, just even assume that A is a non-empty closed set. So, two non-empty. A non-empty closed subset of our Banach space X. That means A on its own complete also. Capital B, another closed subset of X. So, then what we have done, in fact our first paper appeared, as I told, I think Sadiq Pasha, my student, and myself in 1997, Acta Science Math, then 2000 approximation theory. So little later, jointly with Professor Kirk and my other Anthony Eldred, we generalize the non-expansive map. I mean that if it is a weakly compact convex subset of a Banach space, instead of normal structure, we introduce a concept called proximal normal structure. Then we can find a point x, is the distance between x and Tx equal to distance between A comma B. That appeared in Studio Mathematica in 2005. Then previous class, I told what is the contraction, cyclic contraction. Yeah, just with this motivation I will stop. B will not take like the previous case. Will not go for complicated thing in the beginning, just a shift translation of that. Capital B equal to set of all x plus h, say that x belongs to A, fix h belongs to capital X. A vector h is h, or you fix x naught, a vector. This is our set B. Suppose T from A to A something, it is contraction or non-expansive, whatever you like. This is B. Like there, now I have a map T from A to A. Now I want to define a map from A to B as Sx. What is the natural way? Any element in B will be of the type x plus h, but x is where? In A. X is in A mean I know what is Tx. Again Tx in A mean Tx plus h will be in, instead of x, Tx, that is also in A. Then this will be in B. Okay. This is our Sx. Now what is norm of Sx minus Sy? Sx equal to Tx plus y, Sy equal to Ty plus h will subtract, that will get cancelled. In fact, isometry. So norm of x minus y, correct? T norm of I am checking again, norm of Tx minus Ty. So hence, so T may be a non-expansive map or a contraction map, then S will be also a non-expansive or contraction map. Okay, forget about that. Suppose T has a fixed point, Tx equal to x. It has a fixed point, Tx equal to x. What can you say about Sx? Sx by definition x plus h. Sorry, S Tx, that's what I will write, Tx plus h. Then what is norm of Sx minus x, distance between Sx and x. Sx equal to norm of Tx plus h minus x, but what is Tx? X. Tx equal to x, x plus h minus x equal to h, norm of h. So what should be your nice choice of h? Select a h such that norm h is 0, okay. If it's 0 means B will coincide with A. But what we want to find a point x in A such that distance between x and the image Sx equal to distance between the set A and the set B. But what we are getting? Distance between Sx and x equal to norm of h. H is our choice. We have fixed a h such that h is in our Banach space. So select h such that norm h equal to a real number. Norm is length. So find, okay, exercise. So check whether you can find a h such that norm h equal to distance between A and B. So then yes, we are, this is a, whether it is non-expansive or, I mean, that is the need. So that's why it is easy to work in best proximity point theorem. Of course, we started with not for, this is called parallel. A is vertical line type, B vertical. In fact, Espinola, after our paper in 2005, Espinola from Spain, he generalized, we have given two main theorems in Studia Mathematica. He generalized one of our theorem using some other concept, and he used this type of map, discuss this type of sets called parallel set for a strictly convex Banach space like that. Just here I wanted to give you a motivation to see, first understand in a very simple way, then don't stop with that. Okay, try your best to do some good research work and all the best. Basic thing is, don't neglect the basic thing, then we cannot do any reasonably good work also. Understand the basic concept, give any number of time to understand the definition and the concept, then try to do good work. All the best, and again would like to thank the organizer for the nice opportunity, all of you, not only professor.
Thank you, sir. Thank you very much. I think because we are about to complete all the talk session, so thank you very much, sir, about this
Thank you.
elementary but very important concept in the area of functional analysis, best proximity point. So this time we are not allowing the question, or maybe one or two questions we can have if you have them. Yeah. Is anyone in this talk?
Even if you don't have time, after the valedictory,
Yeah, you can. Yes. Then you can have. So thank you very much, sir. Now after a few minutes, we will have the valedictory session. Thank you very much. हेलो 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 हेलो
ऐसे कर लो, उसको उस साइड से ले लो, मैं इधर ले लेती हूँ, बोलते नहीं बनेगा। पकड़ो उधर, मैं तो सुन नहीं पाई। ये सीट वाला लाइन नहीं बोल रहा है ना, ये सीट वाला लाइन नहीं बोल रहा है। मूर्ति सर, वृंदा सर्विस नहीं है, स्टार्ट कर दे। हो गया।
As our guests have arrived, a very jestful good afternoon to everyone. My name is Dipshika Paul from MSc Mathematics 3rd semester.
And my name is Pushpalata Thakur from MSc Mathematics 3rd semester. As we reach the culmination of this insightful workshop, Global Initiative of Academic Networks, let's take a moment to acknowledge the brilliant minds who shared their expertise, and special thanks to everyone who were part of this event.
As it said, anyone who stops learning is old, whether at 20 or 80. Anyone who keeps learning stays young. And our chief guests are proof that they are young-minded experts.
To proceed the program ahead, we would like to invite our honorable chief guest, Professor Amit Kumar Saxena sir, Director of IQAC, and experts, Professor P. Veeramani sir, Registrar, Professor A.S. Randevi sir, Course Coordinator, Professor P.P. Murthy sir, Local Course Coordinator, Rao sir, and heads of mathematics and CSRT department to lighting the lamp to worship Goddess Saraswati and pay tribute to Indian mathematician and number theorist Sir Srinivas Ramanujan.
सरकार भी नहीं बोलना नहीं हाँ छोड़ो केंद्र सरकार नहीं बोलना फिर आप फिर हमारे सबको बुला लें फिर मेरा सबको बुला लें नहीं मेरा
Padma
नहीं नहीं इनका नहीं है, वही तो बोली बुरिंडे मैम नहीं है। अच्छा उनका भी नहीं, हाँ आपका है, फिर मैं बोल दूँगी ठाकुर सर को, वी वुड लाइक टू इनवाइट। Following this, we would like to invite Professor P.P. Murthy sir to honor our Honorable Professor Amit Kumar Saxena sir with bouquet. ताली वाले नहीं बजाते, अल्लाह ताली बजाओ भाई।
Next, we would request Dr. Dhananjay Gopal sir to honor Registrar of our University, respected Professor A.S. Randive sir with bouquet. In this series, we would like to invite Dr. J.P. Jaiswal sir to honor with bouquet to our... Okay, sir. We would like to invite Dr. Manish Kumar Gupta sir to honor with bouquet to our another chief guest, Professor P. Veeramani sir.
Next, we kindly request Professor A.K. Thakur sir to honor our chief guest, M.C. Rao sir, local coordinator of GIAN program.
Now, we would like to invite Professor P.P. Murthy sir for welcome address.
Now that our foreign expert Besle sir have arrived, I would like to request P.P. Murthy sir to honor our professor.
Good afternoon, one and all. Honorable Professor Amit Kumar Saxena sir, Honorable Vice Chancellor and Director IQAC and Senior Professor of the School of Mathematical and Computational Sciences, Professor Basile Brende, mathematician, Senior Professor from Romania, Professor P. Veeramani, Senior Professor, IIT Madras, Chennai, Senior Professor of Mathematics Department, Professor A.S. Randive, Registrar of our university, Professor M.C. Rao, Civil Engineering Department head, our department head, Professor A.K. Thakur, the former R&D chairman, Professor Bhaskar, Dr. Ratnesh, my colleagues, Manish Kumar Gupta, Dr. Dhananjay Gopal, Dr. Koti Varaprasad, Dr. Uma Devi Patel, my computer science colleagues, research scholars, participants, MSc students, office staff, I welcome you all on the finally awaited the last of this program, that is the GIAN program under the title Recent Trends in Metrical Fixed Point Theory and Applications, which was initially submitted with my another project of probabilistic metric spaces in 2018. But at that time, my only one project was funded, that is on probabilistic metric space, and that too also a Romanian mathematician from the which university, sir? West Timisoara. Yeah, Technical University, Timisoara. No, he's Cruz. No, this is yours, Professor. Yeah. So he delivered all the talks during 2018, and the second program, which was actually, as I said, submitted in 2018 itself. At that time, I requested Professor Brinde to send the details. We have submitted jointly at that time, but we don't know what happened in between. Corona also 2 years, and finally one day Professor Rao called me and said, sir, one of your project is in the air and they are asking the recent consent from your foreign expert. I was suddenly shocked because you see 2018 and this is 2023. Immediately I wrote to Professor Brinde and he sent the consent very generously. Since I had his CV of 2018, he updated the CV also. We have not changed the title itself. Title is more or less same. There is no change in the title. And finally, within 3 to 4 months, our proposal was accepted, got the acceptance from IIT Hyderabad. And after that, we had planned to organize this beautiful workshop during November 11 to 15, 2024. But the professor was having, I think each one of you understood very well that his schedule is very, very hectic. And Professor, we are very grateful that you are here all the 5 days, even from your hectic schedule. From here he was working for 3 days continuously, all the afternoons he was working for his country. So you can understand how much important he is for his country. He is the national coordinator of accreditation in mathematical sciences of Romania. So that is the little bit story of this program. So to welcome, I must thanks to our Honorable Vice Chancellor, Professor Alok Kumar Chakrawal. Really, his constant support, his constant monitoring, his instructions to all the people, all the office people, and all the supporting staff to support the GIAN function should be successful. So due to some reason, he is outstation today also. So I must take this opportunity to thank on the behalf of the School of Mathematical and Computational Sciences, on the behalf of the Department of Mathematics, and on my own behalf, we are gratitude to Professor Alok Kumar Chakrawal for his efforts to supporting us, and we reached up to this level. I must welcome to our chief guest of this program, president of this program, Professor Amit Kumar Saxena. As I said last time also, he is the senior most professor of School of Mathematical and Computational Sciences, lot of work in data science, and recently he is back from University of Thammasat, Thailand. His work is immense in computational sciences, and from time to time we used to discuss, and he is very friendly with all of us, even the student or the faculty members. I welcome you, sir. Our most dynamic, quick decision taker, and no file on the table. This is what the smartness of my own department, senior most professor, registrar of this university, my very good friend, Professor Abhay Sharan Ranadive, who is very, very enthusiastic to know about the growth of this program right from first day to till end. Whatever I used to post, I think hardly I find a minute to get his response immediately. I welcome you, sir. As I said initially about Professor M.C. Rao, since the GIAN started or given to as a nodal center, am I right, sir? Yeah, nodal center in the India. So, Professor M.C. Rao is the local coordinator for Guru Ghasidas Vishwavidyalaya, Bilaspur. His support is immense. His actions are very fast. And you just request or your problems you put up in a proper manner. He is very commendable to take the action immediately, or in case enable to solve such problems, forwarding them to the highest authority of GIAN, that is national level, national coordinator. I welcome you, sir. My very coolest, I can say that, professor of the department, head, A.K. Thakur, who is, I don't find that when he become angry, I wanted to see actually. Sometimes I feel that because of my actions, many get angry. But this is a man who always, whatever I say, smiley face ho jayega, sir. So this is what I welcome, my dear friend. Deans school of various schools of this university, we have total 11 deans. Professor Rajendra Mehta, who is very dear to us and particularly dear to me also. So I welcome you, sir. Various heads of the departments of this institute. We have total 32 departments in our university, 11 schools in our university. I have to say a few words about the Professor Bhaskar. He was earlier heading the director NAC, and under the immense dynamic leadership, this Vishwavidyalaya got A+ grade. And at that time, Dr. Bhaskar was the director. So, apart from that, because of the R&D, now Professor Srivastava is the head of the R&D, but earlier he was the head of the R&D. Since this comes under the R&D, so Professor Bhaskar, I welcome you. Zoida Birende, she is the better half of our very good friend, Professor Birende. For the past 6 days, I can say, Today is the 6th day for me, 7th day for me, for you maybe the 5th day, 5 days. So, I can't explain actually how these people are. And in the Indian scenario, in the Indian context, if I can say, I don't find any difference between our society, our family and their family. They are living with their 2 daughters. Professor Birinde, he is living with 2 daughters and 4 grandchildren. So sometimes we have a different philosophy about the central universe and the western worlds. So last time also when I met Professor Dorel Mehaj, the same, and this time also same. Sometimes we feel, sir, you should be adopted in India. So Mrs. Zoeda Birinde, who is professor of chemistry, and as professor said in one of the lecture that his one of the chemistry teacher used to do lot of problem, creating lot of problem to him, and finally she was very happy that he married to a chemistry teacher. This is the, in Indian context, Indian scenario, taken the revenge properly. So, I welcome you, madam. You are so dear, so nice, all the 6-7 days with us. She has some English speaking problem, she can understand very well, because she has no need to move like Professor Brende is used to move here and there. I have to say my research scholars, entirely they worked, sir, entirely. What I say about them? Some people may feel that Murthy is very busy. No. I am busy on how to manage. I am not busy to do things. It was done. And this is done because of my research scholars, my department research scholars, and some of the outside scholars. I am really thankful and I welcome you all. Really, it is very interesting that normally PG students, they used to sit for some time. If lessons are in the classroom lessons, they understand that in future and the end of the semester, they have to write exam. And for that exam at least, if the teacher is good or bad, teaching good or bad, we have to sit till all the 60 minutes. But really, I appreciate not only your patience, I appreciate your ambition, I appreciate your zeal, I appreciate your motivation sometimes. Thanks that you are all the time you are here and supporting us like anything. All my research students, yeah, we should have a clap for these students at least. Thanks. And thanks to all my research scholars who were here particularly. Without them, this Murthy is nothing. And today I really appreciate them. They are my shoulders. Thanks to all my research scholars, without saying anything, but just understanding my feeling on my face, they understand everything. Thanks to every research scholar of me, even my own faculty member who was my research scholar. As far as the finance department is concerned, they supported a lot, they helped a lot, thanks to them also. VC office, registrar office, then this auditorium, then all the faculty members of the mathematics department, all participants, really you participated very well, and like as our professor Brende said, really your understanding is excellent, and the questions you used to ask even in the guest house, in the tea, even during the lunch hours, this is the way how to learn things. And thanks to the auditorium employees and the supporting staff. One more thing I have to say, the whole program is videographed, webcasted only with 15 to 20 seconds delay. We have this program on Zoom also. I must thanks to 2 participants who were daily sitting for our lectures at a distance. One is from Bahrain. I must thanks to him, might be online. And another is from Uttarakhand. The girl's name is Poonam. So I must welcome these 2 also. So the whole program is on YouTube, and anytime, any day, you can see that it is already streaming. This is all the, each day, sir, we have 7 hours recording minimum, each day. So total 5 days, the recording is not less than 35 hours, that too also HD. So this is what you get, each and everything, whatever incidents happen in this room number 1 of this auditorium building, written on this board, or the presenter presented in this. I must thanks to our 5 speakers, including me, Dr. Dhananjay Gopal, Dr. Jayaprakash Jaiswal, Professor Vasily Birende, and Professor Veermani. Especially Professor Veermani, like Professor Birende says that really you are genius, because there are certain concepts you innovated. This is our really luck to see such people, because in function essays, when we talk about Kirk, Billy Sims, etc., so you can understand what is the height of this professor, who is very, very simple in nature. Even he used to go by our university bus to meet the participants and to give a feeling to the participant, I am among you. Thank you, Professor. Professor Vasily Birende, he also the same. Sometimes I thought that he may be little bit having some aggression, but for the past 7 days, I am looking at you, sir. Really, you are so generous. Really, you are a genius of Romania. He is one of the Ramanujan of Romania. What mathematics he does, what not he knows. Each and everything he has done in analysis, particularly the nonlinear functional analysis. We are very grateful to you, sir, that you are here. So, last but not the least, as we say that for the success of every man, a woman must be there. And I am here seeing that this Zoeta Binde is very silent, she is very keeping mum most of the time, and that's why this man can speak very well. So, I am very thankful, madam. I am very thankful, madam, for your generous nature. You can continue it when you reach Romania. Thank you very much. Thanks to all for giving me the chance and opportunity to speak about the whole GIAN program, which is successfully completed till time. Thank you very much. Thanks a lot.
Thank you so much, sir. Now, as Professor Zoeta Brinde ma'am has arrived, I would request Dr. Uma Devi Patel ma'am to honor with bouquet to respected Professor Zoeta Brinde ma'am.
Now we would like to invite local coordinator of GIAN program, Professor MC Rao sir, to share his wisdom.
Honorable Vice Chancellor in charge, Professor Amit Kumar Saxena, the Registrar, Professor A.S. Randive, the resource person, Professor Berende and Professor Veermani, the head of the Department of Mathematics, Professor Thakur, and the course coordinator, Professor P.P. Murthy, all the faculty members of the School of Mathematical and Computational Sciences, and dear student participants. A very good afternoon to all of you, and welcome you all for this valedictory function of GIAN course on recent trends in metrical fixed point theory and applications. So generally valedictory means we have to summarize the things. Now we have come to an end. So any program, whenever you organize that program, there must be some takeout from the program. I hope that you all have benefited greatly from this course, which was conducted from the last 5 days, from 25th to 29, from the knowledge shared by both the professors along with other faculty members who taught during this particular course. So the main objective of this GIAN program is to get an exposure for the Indian students with a foreign resource persons so that they can acquainted how the research is going on in Western countries or in other abroad countries, so that we can also go forward to carry out the research in those areas also. So that is what we have provided. The GIAN, National Coordinator GIAN has provided an opportunity for us to have and share the knowledge from the experts from Romania as well as from the retired professor from IIT Madras. So actually this is the first course under GIAN program, GIAN phase 4. Earlier we had conducted 7 programs under the GIAN, phase 1, 2 and 3. And of course I think Professor Murthy, this is the second course he conducted. Earlier in phase 3 also he has conducted 1 program. So now this is the beginning under phase 4. We will go with more, we hope that we will have more courses in near future. And of course in the month of January we will be having 1 more course in social work department that is recently sanctioned. So maybe in the 3rd week or 2nd week of January we will be having 1 more course under the same program. So I request Professor Murthy, because another objective of this program is to have the collaborations with the foreign universities. Since now the course coordinator, this is the course, second course he is conducting, and I request both the professors from Professor Murthy and Professor Berende, we must have some collaboration kind of thing. You have to explore the possibilities for some collaborations with the Romania University so that the students of this university get benefited from these collaborations. So at last, I should congratulate Professor Murthy for success and his department, Mathematics department, for successfully conducting this program. And without your participation of the participant, this program would not have been successfully completed. I also thank the administration, Honorable Vice Chancellor, Professor Alok Kumar Chakrawal, and Professor Randive, the registrar. Without their support, this program would not have been completed. At the end, I thank the organizing team for giving me the opportunity to speak few words in front of you. Thank you one and all.
Thank you so much, sir. Then we would like to invite our respected Professor Basile Brende, sir, to share a few words about his experience with us.
Hello to everybody, good afternoon. Well, I just want to confess that at the beginning I was thinking, wow, I have to spend 6-7 days, a lot of time here. And in the end now, I feel it was too short, this program. So, Professor Murthy, next time I suggest you a program of 2 weeks. Okay. Unfortunately, I could afford only 1 week because my tough agenda, so I am really happy I was here inside this program. Very good conditions, very nice person attending this course. I was really impressed by the audience, by the organization, so my only regret is this one. I could not spend 1 more week here to know more about this area, and maybe this will be a reason to establish some contacts
I promise I'll contact our person who is responsible for international relations to try to have some Erasmus agreements, and this is the starting point for possible visits of in both directions, Romania to India, India to Romania. So thank you. I hope it was interesting for you. The attendees, it was useful, and be in touch. As I told you during the lectures, please don't hesitate to contact me if you need some answer to your questions, but be patient. My answer can wait 1 week, 2 weeks, and so on, because I explained to Professor Murthy next week is also full of activities, and this is the reason I could not stay more here. Thank you very much. Congratulations, Professor Murthy. And once again, I want to repeat what I said in the opening ceremony. I'm deeply impressed by the fact I was in the team with Professor Veramani. He did some deep contributions to our area, very important contribution. I am really proud of being in the same team with you. Thank you. Have a nice return to your homes.
Thank you very much, sir, for taking the time to share your wisdom and experience with us. Now for the feedback, I would call Dr. Rashmi Kevit ma'am to share her experience.
Good afternoon, everyone. My experience is, this is the very excellent combination. Professor Veeramani sir and Vrinde sir, I have seen here pure and applied mathematics. I have seen fixed point theory in another way, but here I have seen fixed point theory in a visualized way, in a mathematical modeling way, in a programming way. So all this possible because of Vrinde sir and Veeramani sir. So we have to understand things applied way as well as theoretical way, because both are essential. So here I understand. So thank you so much, sir. So this opportunity provided with this GIAN course, sir. Thank you so much, sir.
Next, I would call anyone from Nepal to share his feedback.
Our honorable chief guest at the ending session, and all the participants, researchers, research scholars, and PGA students, master's students. Thank you very much, and I especially gratitude and my heartily thanks to organizer and all over the entire team of the GIAN, and especially Dr. P.P. Murthy sir, and especially our expert, Vrinde sir and Veeramani sir. Thank you. This program is very, very beneficial for us, like as those students who is just increasing towards the research and want to do research. So I feel here very nice, and I learn here so much things related to research, trend of research. So I am very grateful to Professor Dr. P.P. Murthy and along all of their entire team. Thank you very much.
Next, I would call anyone from Aligarh Muslim University to share his experience.
First of all, I want to introduce myself. My name is Ahmed Farad Razi. research scholar from Aligarh Muslim University. And I am very grateful to be here, that professor give us a chance to be the part of this marvelous program. And I congratulate him for the successful accomplishment of this program. And I want to thank Professor Veeramani and Professor Brinde sir to provide us the valuable knowledge of what best he can provide us. And in the end, for the hard work of Professor Murthy sir, I want to say share from ghazal of Bashir Badr Sahab. जब से चला हूँ मंजिल ही पर मेरी नज़र है, मैंने मुड़कर कभी मील का पत्थर नहीं देखा. मील का पत्थर इज अ माइल्ड स्टोन ऑन द हाईवेज. जब से चला हूँ मंजिल ही पर मेरी नज़र है, मैंने मुड़कर कभी मील का पत्थर नहीं दिखा. तुम समझते हो कि ये फूल मुझे विरासत में मिले हैं, तुमने मेरा भी कांटों भरा बिस्तर नहीं देखा. थैंक यू वंस अगेन.
Thank you everyone for sharing your experiences. Next, we would request Professor P. Veeramani sir to share his experience with us.
Yeah, thank you very much for the wonderful opportunity to come over here and meet all the participants and all the senior professors and experts. Again, I would like to congratulate Professor Murthy and all the team members from the department and other department research scholars, participants, for making this very, like, we are like staying in a home and sharing the experience. We enjoyed the hospitality as well as meeting the students, research scholars. I enjoyed. I do hope something you will take as Professor Berende, such a lovely algorithm, various algorithm Professor has given, and if that will motivate both, as some of you say, concentrate both on theory as well as algorithm, a basic concept understand and do good research work. And again, I would like to thank you all for the opportunity and wish you all the best. Thank you very much.
Thank you so much, sir. We feel very privileged to learn something from you. Nextly, we would request the senior most faculty member of mathematics department and presently registrar of our university, respected Professor A.S. Randive sir, to share his wisdom.
Thank you. Professor Amit Saxena, who is discharging the duties of in-charge Vice Chancellor and sitting in front of us, has been my colleague and friend for many years. I joined this university in 1989 and he joined in 1990. So I welcome him. Professor Berinde, I hope your stay was comfortable over here. Although Professor Murthy must have tried and should not have left any stone unturned to make your stay comfortable over here. I hope it was really comfortable. Thank you, sir. Professor Veeramani, there are two words, but he's a little bit different from them. Veer in Hindi means brave, and Mani means the best one. The person sitting in front of us, named as Professor Veeramani, is very, in different way is Veeramani. The best part I have observed, rather I have been observing last 15 years or so when I visited him for the first time, such a humble person, such a noble person, such a learned person. I am happy to note that the two experts who have visited our university in GIAN, both of them are full of appreciation for each another. This is possibly the nature of mathematics. mathematics itself makes you a little bit humble. Sitting on the dais, Dean, School of Mathematical and Computational Sciences, Professor P.P. Murthy, Professor Rao, Professor Thakur, and sitting in front of us, Professor Joyita Birinde, Professor Bhaskar, Professor Mehta, other teachers of the Department of Mathematics, and dear students. I really miss that I am not discharging my duties as a teacher in Department of Mathematics, and I have been assigned some academic and non-academic works. Partially when I was director IQAC for last 7 years or so, it was something like academic duties also, compiling the academic data, and that is the best part. I can say I was not compiling any other data, but I was collecting and getting compiled the academic data of the university. And now when that job was over, and we could get successfully A++ grade under the leadership of our Vice Chancellor, I was assigned yet another duty of Registrar Guru Ghasidas University, Bilaspur. So I am missing my lectures. But now once again I will like to focus what is your take home today. After an exercise of 5 days, what you are taking home back with you. Apart from the knowledge that you are going to take with you, that you have noted in your notebooks, and you will be collecting it and recollecting it once again and again from YouTube and other resources. But the things which you will not be able to learn once you depart from these two experts, how mathematics is learned. How mathematics is learned, this is one part, and how mathematics is discussed, this is yet another part. Learning mathematics and discussing mathematics is quite far away thing from teaching mathematics. Teaching mathematics makes you feel some sort of burden, that I have to deliver this much of the portion of the syllabus in these many minutes, and the students should be mostly satisfied. We go for a curve. Some of the students on the average line, some of the students above average, and so on and so forth. And while I was discussing these ideas with Professor Veermani just for 1 or 2 minutes, which I could get with him, I asked simply a question to him, sir, what is the difference that you feel between the students in IITs and the student in this university? I was happy to note that he said everything is same. Everything is same. The students are equally interested over here. They are ready to learn. But then we have to think what makes the difference. Why certain students, why certain professionals reach to the best of the institutes in India and abroad, and why some of us do not reach over there. Possibly there is the difference that how you discuss mathematics. How you learn mathematics, it depends on your teachers. How you understand mathematics, it depends on you. But how you discuss mathematics is a teamwork. And mathematics believes in working together. Inasmuch as you discuss with others, it is not that others learn from you, it is that you learn from others. I hope this lesson, which has been imparted by our two experts to you, directly or indirectly, and which I am summing up in words in a different scenario, because I am not talking about mathematics, I am talking in the capacity of registrar at present, that this makes the difference. And this is what it should be the real take home. When you go home, when you interact with any of the
person who is interested in learning mathematics and learning something from you, let's develop the attitude of discussing. So thanks for calling me over here, and thanks to allow me to share my views with you. I'm happy to see some of the old students from this department, some new students sitting over here, and some research scholars. So thank you everyone, thanks.
Thank you very much, sir. Now we would like to invite Honorable Chief Guest Amit Kumar Saxena, sir.
Thank you. Respected Professor Brende, Madam Joyita Brende, Registrar Sir, Professor Biramani, Professor Local Coordinator, Professor M.C. Rao ji, Professor P.P. Murthy ji, Professor Thakur Sahab, the Deans of the schools, Head of the Department, Dr. Dhananjay Gopal ji, participants from different other places. Professor Brende ji has to leave for his airport, so I will not take much time. I wish all the very best. Congratulate Professor Murthy to arrange this program, and throughout the 5 days, because I was sitting in the next room, next building, that is IQAC building, same building but next room, I must say. So I used to see that till morning till evening, from morning till evening, I used to find the participant, Professor Binde, and all the experts talking and discussing outside the auditorium about the topics, about the subject. So I really feel that this is going to be a very successful story of the whole event, and I dream that our university will collaborate with the technical university from Professor Brinde has come. So after reaching there, we will do efforts. Professor Murthy will take initiative to collaborate with some in the more efficient way and in the more fruitful manner. I wish that all the participants have a good stay during these 5 days here. All those participants, especially who came from outside, I will urge that they can visit around also, take a look at the campus as well as some nearby places if they have time, if time permits them. Thank you very much, and congratulations once again.
Thank you very much, sir. Now I would like to request Professor P.P. Murthy, sir, to present memento to Professor Basile Brende, sir.
Sorry for leaving. We have to leave at the airport.
And then I would like to request Professor A.K. Thakur, sir, to present memento to Professor P. Veeramani, sir. I would request Dr. Uma Devi Patel, ma'am, to present memento to Professor Zoita Brinde, ma'am.
ये बोलोगे आप A.K. ठाकुर सर बोल देता हूँ।
And then I would like to request Professor A.K. Thakur, sir, to present memento to Professor P. Veeramani, sir.
Then I would like to request Dr. J.P. Jaswant. Yes, sir.
Then I would like to request Dr. J.P. Jaiswal sir to present memento to Professor M.C. Rao sir.
Now we would like to invite Head of Mathematics Thakur sir for vote of thanks.
Now we would like to invite Head of Mathematics Department, Professor A.K. Thakur sir, for vote of thanks.
Thank you. Now it is the time of validations, so without delay, Hannah. I feel honored and privileged to get the opportunity to propose a vote of thanks to this GIAN program. I would like thanks to honorable delegates, invited speakers, who blessed us with the presence and completion of 1 week GIAN program successfully. I, on the behalf of Head of Department Maths, convey the deep rewards and heartfelt thanks to our Honorable Vice Chancellor, Professor Alok Kumar Chakrawal sir, for his constant help, blessing, motivations and guidance that radiates the source of energy to formulate 1 week this GIAN program. Thank you once again, sir, for your blessing and support. I am thanks to respected Professor A.K. Saxena sir for his presence and blessing and motivations. I am thankful to respected Registrar sir and all respected members as they have helped us to administrative and approval for organizing these events. My special thanks to Professor Virendra and Professor Veeramani and other faculty members from different places for his gracious presence. I would also thanks to course coordinator Professor P.P. Murthy for their constant effort for organizing this 1 week GIAN program successfully. I am thankful to our faculty members, research scholar, PG students, non-teaching staffs who always stand with us and motivate us. Thank you all for making this GIAN event successfully. Thank you all.
Thank you, sir. Sorry, sir, we would like to apologize. I would request A.K. Thakur sir to present memento to Professor Amit Kumar Saxena, sir.
Now, I would request Dr. Koti and V.V. Varaprasad sir to present memento to
Certificate distribution.
We would request Uma Devi Patel ma'am to present certificates. Dr. Rashmi Kevat, Kavita Patel, Rahul Mansotra, please clap.
Rahul Mansotra.
मुस्कान पटेल,
पूनम का नहीं बोलना है ना.
मंजरी देवांगन, अशोक पटेल, नंदू प्रसाद कोइरी, दिलीप कुमार शाह, उदय कुमार कर्ण, टिकेश वर्मा,
बोलो जल्दी नाम बोलो।
टिकेश वर्मा हटाइए मैम उसको, मिस्टर मोहम्मद जुनैद, मिस्टर अहमद फरज राजी,
पकड़ लेना
नीचे वाला तो
मैम, नीचे वाला मैम एक और है,
विनीता चंद्रा,
पूनम पता नहीं मैम कौन है।
तोशन कुमार श्रीवास,
मैम ये मेरा ही है।
दीपशिखा,
नहीं मैम दूंगी ना मैं। चलो ना तो जाओ ना।
दीपशिखा पॉल, टंकाधर साहू, कविता चंद्रा, कुलदीप साव,
मिस्टर हपका सुरेंद्र,
सर,
तुषार, श्रुति गुप्ता, राम जीवन, प्रियंका साहू, मनमोहन सिंह,
सब किए जा रहे हैं फोटो क्लिक। नहीं है, अमन तो ये है।
सभ्या साहू, आशीष कश्यप, डॉक्टर पुष्पलता साहू, प्राची पटेल, विनय मिश्रा, चंद्र प्रकाश धूरी सर, वेद प्रकाश पटेल, अरीना कजू,
जो भी है।
ये ऋतिक का है मैम। पुष्पलता ठाकुर, दौमणी दनसेना, बरखा सिंह, रेणुका देवांगन, संकर्षण नायक, आनंदा साहू, आकांक्षा यादव, ऋषिकेश पटेल, आदर्श तिवारी सर,
खत्म हो गया यार, हो गया यार बहुत। नहीं है, लिख देंगे सर बाद में। सर आपका दे रहे हैं बाद में।
मेरा है ही नहीं, मेरा भी दे दे। कहाँ है मेरा? कोई लेके चला गया है लग रहा है। हाँ लेकिन नाम ये चला गया होगा तो
We would kindly request everyone to raise from their seats for national anthem. National anthem. जन गण मन अधिनायक जय हे भारत भाग्य विधाता, पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा, वृंद हिमाचल यमुना गंगा उच्छल जलधि तरंगा, तब शुभ में जागे तब शुभ आशीष मांगे, गाहे तब जय गाथा, जन गण मंगलदायक जय हे भारत भाग्य विधाता, जय हे जय हे जय हे जय 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 हे। Thank you, sir.